super excited to see everybody today. What a great turnout. Takes a lot to put this together, but you know, we made sure Will at the ballroom here made enough food for you guys because we know farmers know how to eat. So, but we're excited to have you here. We got a great lineup of speakers. I think there's definitely something for everybody here to learn, you know, pick up 2 or 3 things that you can bring to your operation right away. If you're like me, you know, it's, I need to hear things like 2 or 3 times before it starts to sink in. My wife says that it's like sometimes you need a baseball bat to get it through your head. So, but no, I think you enjoy it. You're not, there's going to be things you hear here that you've heard before, but I think there's definitely some things that that you haven't, and it's going to be a different perspective. So, but I'm excited for it. And but before we get started, I think we need to answer a question that many of you have probably thought of once or twice throughout your life, and I think we got some evidence to help answer that for you. And yes, the bears definitely do poop in the woods, so we got that cleared up. So why are we all here? You know, multiple reasons, I believe, and you know, we're going to be talking a lot about tillage, soil biology, what happens in, you know, below ground with the root system. Jim Martindale in the afternoon is going to go into a lot of things regarding tillage and how that works with the, he's going to talk about things like the rhizosphere, things like that. But there's multiple, you know, I guess why change in your operation? This was out in the Successful Farming magazine in 2016. I'm sure you guys hear a lot about this, you know, meet your new boss, the millennials. They're taking over the guard from the other generation, and they're very much about where their food comes from. They want nutrient dense foods. They want to know where it's coming from, where it's sourced from, and that's kind of changed in a lot of things because you know, the consumer is the boss. So another that plays into that, so they're putting pressure on these food companies. These are some of the major food companies in the US. And so they're looking at things different, and they're, you know, wanting to connect with the farmers. You know, you got PepsiCo, Walmart, ADM. Some of you here grow birds for JBS. So that's kind of making you guys look at things too on your farm. And this is real because just recently, working through a company called Arva Intelligence, they're connected and they're looking for 20,000 acres in Minnesota for regenerative soybeans in 2023. And that was through Nestle Food Company. So this is, and there was some real money behind that. And so yeah, there's a lot of these kind of things that are changing the way we look at things. And then you have the old other thing of, you know, the carbon credits through different government programs, whether you agree with them or not. Those kind of things are coming, and it's making that's factoring into our decisions. But our team, you know, at Anez Consulting, we've always, what we're excited about, we're passionate about, we've always looked at trying to solve problems that you guys may be dealing with and try to help you guys be more profitable. We've never been about looking at symptoms and treating symptoms. So we see some of these concepts within regenerative ag that we think are really valuable in terms of helping you guys, or new testing methods, new things of looking at soil and plant nutrients that we can help you be more profitable. There's a lot of buzz around you know, regenerative ag, cover crops, all that kind of thing. And that's all good, but the bottom line is you guys need to be more profitable. You know, less stress in the operation on financials and things like that. I think some of the proof in that is whether you call it regenerative ag or what, but some of the concepts, you know, we got Russell Hedrick, you probably have heard of him in 2022. He broke the dryland corn yield record at 459, and he did that using a lot of these principles. So it's a real thing. It's not just fluff. And this is being done at scale in small operations and large operations. So whether looking at, a lot of us, maybe you're in a conventional type system, and if you think some of these things are for you to look at differently, it's definitely a mindset shift. So when we look at the soil, we look at like a four-legged stool, and that's a sturdy stool. We look at the physical, we look at chemical, we look at water quality, whether that's rain or irrigation water, and then the fourth thing is the soil biology. That's one thing that the biology part that we haven't done as good in the past, partly because there's a lot of new research on soil biology. We always, as farmers and agronomists, we've known about that, obviously, and we know there's a biology component, but we haven't understood it as well. And but in the last 10 years or so, there's a lot more research on that, and Jim Martindale will talk some about that too. Some recent research coming out of Australia in the last 10 years. But in addition, like the Haney test is one thing that really helps us to look at that. But so what we always say is, if you can't measure it, you can't manage it nor improve upon it. So like your businesses have changed immensely over the years. Ours has changed too. Looking back 20 years in 2004, as far as how we address soil and plant fertility, we're primarily, we had the soil chemistry test, plant tissue testing, analyzing irrigation water, and then manures and limes, as well as, in-field observation. Fast forward 20 years, so we have a lot more in our toolbox to work with you guys to get you to the next level. So we're looking at things like soil health testing that I mentioned, the Haney test that was developed to really help us measure where we're at biology-wise. We're doing a lot more soil DNA testing to, it's a pretty in-depth test that shows, hundreds of parameters within your soil. Soil paste test that works well to identify problems and to use on sands to show what's actually in soil solution. And then plant sap analysis has been a game changer for us to really understand what's going on within the plant. And then the PLFA test is to help understand the fungal bacterial ratios in the soil. And these are some of the labs that we partner with to accomplish that. Trace Genomics out of California to help do some of the DNA testing. One of the speakers here today will talk about using the bee crop test. It's another DNA test to help quantify what they treat in the manure and then applying that to the soil. Regen Labs out of Nebraska, looking at this Haney test, and then the New Age out of Michigan. There's only three or four labs in the U.S. that's doing plant sap testing, and we use New Age out of Michigan for that. And then Brookside Labs has kind of been our mainstay for doing the bulk of our testing. So one of the kind of neat tests we do is this is a complete nutrient digest. So what the lab does is they bomb it with pretty harsh chemistry to show everything that's in the soil, not just what's plant available. So for example, here, potassium, we're looking at over 4,000 pounds, and that's just in the top 0 to 6 inches. So it's obviously that's not available, and throughout all my schooling, they always talk about what, that's just not available. You can't get at it, but this is free nutrients here, and the reason we can't get at it a lot of times is because of our biology is lacking. We don't have those fungal networks to tap into that where the root here can't. And so that's just one thing to look at. Like this is obviously going to change from field to field in different soils, and but if you can, that's some real profitability if you can change some practices and tap into these nutrients. Plant sap testing, like I mentioned, has been a game changer for us. I didn't really know much about this until the last 5 years, but look at it, it's just like a blood test in humans. So we're measuring the old growth and the new growth in the plant, just the basically the blood within the plant. Previously, we did a fair amount with plant tissue testing, and a lot of times we felt they were more ambiguous. This really helps you understand what the plant is taking up, shows you sugars, bricks, different components of nitrogen, and then all your micronutrients. And more importantly, even the deficiencies, it shows us where we're excess. And a lot of times in agriculture, we find we have excesses in like chlorides, sodiums, and different things that are tying up other nutrients. And obviously, boots on the ground paired with good testing methods are, your best combination. So plants fix soil, fix dirt and make soil. I always thought, and was taught, that the soil is the plant's stomach, that the roots uptaking water, nutrients, and bringing that up in the plant, which is all true. We were taught it takes up nutrients by mass flow, diffusion, root interception, basically the root running into the nutrient. But there's another way that more recent research has showed that's pretty amazing stuff, where the plant actually is consuming the bacteria, bringing it in through the root, consuming it, or through hormones and nutrients, it's calling for, say, I need manganese. And through the biology and the microbes, pulling that microbe in, taking off the manganese, sending it back out to work. So we're farming the microbes. That's what's so exciting about biology. And if you guys never seen this image before, this is a microscopic image of a root tip. And I never really fully understood this till I seen this image. Again, we always been taught, the plant takes up nutrients and water into the upper growth and reproductive tissues. But more than that, about 20% on average of the photosynthetic material, so basically through photosynthesis, you're converting sunlight into sugars, but around that 20% is pumped down through the root system and leaked out into the soil. And the neat thing about that is as you improve your soil, as you improve plant nutrition, you're getting a higher percent of nutrient or sugars and carbon pumped into the soil to feed the microbes in the soil. So like, talking about looking at different systems and how do you get higher yields, how do you get higher quality, things like cover crops and all that are good, and I'm a proponent of that, but sometimes they just don't work in our system in this climate. Maybe that's an excuse, or if you're growing edible beans or potatoes, it doesn't always work. But you can improve your soil, the quality of your soil, the biology of your soil, the nutrition of your soil, by growing an excellent crop, by growing a quality crop and a high yielding crop, because the higher yielding crop you have is going to have a bigger root system, so you have more area that's doing this. And if it's healthier, it's pumping a higher percentage of these sugars and carbon into the soil. So you can, just by growing an excellent crop, high quality crop on its own, you can improve your soils. And just to kind of relate it with with the human aspect, I just think this is a good visual. What we do in the soil and the plant is really connected to us as humans and or if you're feeding animals. This is the plant chlorophyll molecule in the green, and the human blood hemoglobin in the red. And molecularly they're almost identical. And the main thing that's different, obviously, is the iron at the human hemoglobin and versus magnesium in the chlorophyll. So like I mentioned, our mission is to continue to strive to provide solutions to problems in agriculture or things that you're dealing with. And we're passionate about that, and that's why we get excited about things that we can do by understanding what's going on with some of these tools and combining things like the soil health test, plant sap, and good infield observation. But it's definitely a mind, anything you change on your farm, obviously you guys know that. When you change one thing, it changes multiple things. In my experience working with guys that have switched to more vertical till or strip till, especially like strip till, for example, it's great communication between who's doing the strip versus who's planting, how they're entering the field, how are you handling your manure, your solid manure? Well, we might need a different spreader for that. How you're applying your liquid manure, that changes. How you managing your weeds, that's a whole different game. So it's, that's what's exciting about our industry, I guess. It's always changing, and it's always interesting. And as farmers, you guys like challenges, and there's plenty of challenges in farming. So, yeah, we try to avoid the mistakes as much as possible. We don't want those kind of things to happen. So with that, I just want to kind of give you an overview of what we're looking at today. We'll have time after speakers for questions, but we're excited to have all you guys, and now I'm going to introduce Michael Dunn. So Mike is our precision ag specialist. The Smart 4D logo you see there, that Mike is the main brains behind helping us develop that program. We're pretty proud of it. It really has been a big boon for our precision program and how it works. Mike's also our potato specialist. He's been with us, 11 years, I think? Oh, sorry. Minor detail. So Mike came from us from California. Yeah, we weren't even looking for someone at the time, and he kept kind of harassing us, and Renee finally made us interview him, but he's been a great boon to our business and helping us get our GIS program really off the ground, and what he adds as far as his knowledge. And I kind of provide the dumbed down version, and when we need anything technical, we bring in Mike. So welcome, Michael Dunn.
All right, how you guys hear me? Good? So why are we here? Paul alluded to a lot of this, but I think he left out the free lunch. Well, obviously interest in soil health, soil biology, regenerative ag in general is stronger than ever. And there's a lot, just countless products and practices that are being marketed with soil biology and soil health as major selling points. And really the volume of new products coming out every day is just overwhelming. It's a lot to try to wrap your head around and understand what has value on your farm and what has value as a broader practice. We also have new tools to help identify and quantify soil health and soil biology, and Paul mentioned some of those. And these tools can also be used to help understand how these variables change within the field. We have a better understanding of what impacts soil health, biology, and how these relate to crop health, nutrient use efficiency, and marketable yields. So considering that everything is just hitting the market at incredible space, it's, I think, important to take a step back and make sure that we get some of the fundamental things right in the first place. And we all know that soil biology is important. And even if you're using 100% commercial synthetic fertilizers, at the end of the day, you're still at the mercy of a lot of these nutrient cycles that are dependent on soil biology and environmental conditions. So nutrient use efficiency is another term that's being employed by manufacturers to market biological and soil health products. This is something that's quantifiable. An easy example is to take a scenario where you applied 200 pounds of nitrogen to a corn crop, got 200 bushel yield. Your nutrient use efficiency is 1 pound of nitrogen per bushel. Nutrient use efficiency is affected by a lot of different variables. Two main variables have to do with the fertilizer itself that's being used and the soil that it's being used on. Fertilizer rate, source, timing of application, and placement is important. Within the soil texture, organic matter, the soil biology, and especially the soil moisture is important for determining nutrient use efficiency. And while there's a lot of emphasis on soil testing, nutrient use efficiency is not represented on any soil test. So just remember that soil test is an important piece of the puzzle, but it's not the entire picture. So soil moisture drives almost everything in the soil. It drives soil biology, soil health. It can drive and influence crop physiology. It moderates soil temperature, which also plays into the soil biology components. It solubilizes and mobilizes nutrients in the soil, which can then bring nutrients into the plant, or it can push nutrients away from the plant like we get with leaching rainfall events. We also rely on soil moisture to activate our soil applied residual herbicides. And the list of things that moisture is important on, it goes on and on. And it is, at the end of the day, soil moisture is the single most important manageable factor driving yield and soil health and biology. And so as Paul alluded to earlier, you can't manage what you can't measure. And so we need to start measuring soil moisture if we're going to effectively manage it. And so for our Smart 4D management zone system, we created management zones that highly accurately reflect changes in soil moisture, at least in relative terms. If you look at the map in the middle here, right above the Smart 4D logo, that is the management zone map that was created using multiple different layers of information, such as soil brightness, risk of wetness, which is a type of surface flow model, and other layers to help delineate where we have drier soils versus wetter soils and maybe more field average soil moisture conditions. And so going back to that map in the middle, these orange and red colors are our driest soils. The blue and purple are our wettest soils. And the green shades are more field average soil moisture conditions. Here's the same management zone map draped over the 3D elevation model of the field. And so you can see how the management zones correspond with different topographic features, such as the two red and orange features to the left that are the driest parts of the field. These are also highly erodible soils. And then you can see how the blue and purple colors line up with some of our soil field depressions, areas that are high risk of flood stress. So we took that management zone map, and now we've just drawn lines around all those features and overlaid them on the top image, overlaid them over a color infrared picture of the field. And what I really want to point out here is how closely those lines hug conspicuous soil features and do so much better than the soil survey map units below. This is a good example of why we don't use the soil survey maps to inform variable rate prescriptions or soil sampling. They are good information a lot of the time, but they were never intended to inform site-specific agricultural applications of seed or fertilizer or anything like that. So part of our process and modeling for soil moisture changes involves confirming that the maps that we create actually reflect the way that soil moisture variability falls within the field. And all we're doing here on these slides, the top image is the zone map overlaid on the relief, the 3D elevation model. And then below that, we actually measured and quantified the soil moisture at the time of soil sampling and just compared those two maps to see, does this make sense? Is there agreement where we expect there to be agreement? And there is consistently. One thing that's particularly exciting about mapping soil moisture is you're not just looking at differences in water across the field. You're actually creating detailed maps of the microenvironments that define your field and ultimately define field variability. Now, these microenvironments, the spatial properties are the same year after year. The landscape's not changing, the soil's not changing, but the weather does change. And so how these different microenvironments result in different crop behaviors is really weather dependent, but the actual boundaries and areas stay fairly consistent. So there's a couple of examples here looking at corn during wet growing seasons. In this first example here, the image on the left, the red zone, is where we have our lighter, drier, and warmer soils in this field. And the crop is 100% viable, and it's starting to poke out of the ground and starting to unfurl that first leaf a little bit. The green zone, which is a little bit wetter, a little bit cooler, we have good seed viability following a heavy rain event. But because it's cooler temperature, the seed is not off to as fast of a start as it was in the red zone. And then once we get into the blue and purple zones in this field, that's when we're looking at more flood stress. And because it's so much cooler, the actual development of the seed itself is way far behind the red zone, even though this is the same variety, this is the same hybrid, same planting date, same everything. The only difference here, the main difference here, is disparity in soil moisture. This is another corn example in a cool, wet growing season where the red zones are the warmer, drier soils that I have lined up here on the top of this board. And you can see as you go from red to yellow to light blue to dark blue, the size and color of those ears starts to change dramatically. And as far as the soil map units are concerned, that's all the same soil. But our zone modeling shows that there's conspicuous differences even within that same soil map unit. And again, this is the same hybrid, same field, same fertility, everything. The main difference that we have here is just changes in soil moisture that are dramatically impacting crop physiology. There's a lot to unpack with this slide, but what I really want to just focus on is some of the trends in the soil test results that we are seeing across multiple different soil types. This is a heavy soil. Exchange capacity ranges from 17 to 30. A lot of our sands only range from 3 to 7. But a lot of the trends that I'm going to discuss here are similar across these heavy soils and our sands. So the top right, you see the soils themselves pulled from these different zones. So you've got the red zone has it's some of the lighter colored soils. And as you go from red into the greens, you start getting darker soil colors until you get into the purple, which is the heaviest, wettest, highest organic matter. And so again, the red zones are the high, dry, highly erodible soils. And then as you get down and through the orange, yellow, lime, green, and into the blues and purples, you start getting into the heavier, wetter soils. And along with that gradient change in soil moisture, as you go from low soil moisture to high soil moisture, you also go from low organic matter into higher organic matter. Soil moisture often precedes the accumulation of soil organic matter. You need soil moisture in the first place to start to grow biomass. That biomass adds to the soil organic matter. Soil organic matter adds to the exchange capacity. And as your exchange capacity gets higher, the soil's ability to hold more calcium, magnesium, potassium also increases. So that's why you see here with exchange, organic matter, calcium, magnesium, you see similar trends where they start with red at the top and then go gradually down towards those greener shades, because you're going from low to high. And that's why soil sampling by these types of management zones makes sense, because we're actually accounting for these types of changes in the soil with the types of soil maps that we're putting together to create the zones in the first place. That's not always the case depending on where the management zones are being built. So soil moisture drives everything, and that's especially true on the biology side. These are some test results from the trace genomics testing that we've been doing. And it's a fairly expensive test. So instead of soil sampling all 8 zones that I have in the example here, we only sampled the 3 primary zones: the blue zone, which is the wettest, the green zone, which is field average, and the red zone, which tends to be the driest. And as you would probably expect, where we have the most consistent moisture in the blue zone on the left, we have the highest microbial growth rates. As we get into the drier zones, the red zones, we have the lowest microbial growth rates. Oxygen availability corresponds pretty well with soil moisture. The more moisture we have in the soil, the less space we have for air, and so we end up with less available oxygen. As soil moisture becomes depleted, we move into the red zones and available oxygen increases. The fungi to bacteria ratio, this is a different analysis than the PLFA. There should be some correlation with that test, but not necessarily. But we see that with the fungal to bacterial ratio, that also lines up pretty well with changes in soil moisture. Now getting into the plant pathogen side of the soil DNA analysis, we have conspicuous differences in the amount of rhizoctonia. This is a primary disease in potatoes, but it also affects corn and soybeans, especially early season, responsible for a lot of root rots and stand loss. And what's interesting here is in our healthier, wetter soils, our rhizoctonia levels are well below threshold. But as we start to get into the more challenging, drier soils in the red zones, that's where our rhizoctonia really thrives. Anybody that's dealt with white mold knows that the opposite is true. White mold really thrives in the cooler, wetter environments, and the soil DNA test confirms that here. Some fields that we've sampled, we can actually start to find zones that are so wet that even white mold won't thrive there. This now starts to bring up a point about doing variable rate fungicides. So now we've determined conclusively, we know that this blue zone is the right environment for white mold, and we have a high inoculum of that disease in that zone. Well, now it opens up the option for more expensive fungicide treatments that we would never have considered to put across the whole field, knowing that it only would have paid off on a third of that field. And an example of that would be the fungicide Contans. So you can go through with this type of zone modeling and this type of test and have some confidence moving forward that you're putting that product down where you're going to get the best return on investment. So one of the main takeaways here is that while there's all kinds of soil health products and practices to consider, Really, the best thing that we need to make sure that we're doing right now is managing around this soil moisture variable to the best of our abilities. Not saying that some of these biologicals don't have a place on the farm, but let's just go back to basics and make sure that we're doing what we can to manage the most important things first. And when it comes to soil moisture management, there's two general ways to go about that. There's active soil moisture management, like irrigation or variable rate irrigation based off of these soil moisture maps. Drain tiling, tillage, especially conservation and no-till, and residue management, where you're directly impacting the amount of available water in that soil. And then we also have more passive moisture management techniques. This is where we are managing our inputs around the amount of water that's already there. And an example of this, which most guys, or many guys, if they get into precision ag, the first place that they end up starting is with variable rate seeding of corn. And what we end up doing most of the time with that is where we have the lowest soil moisture potential, we end up dropping our corn rates to the lowest, typically around 22, 24,000 on the low end. It depends on your hybrids and your soils and whatnot. Then as you get into the wetter parts of the field, that's where we're bumping up our populations, typically no more than 36,000 for corn. Soybeans are a different animal though, because of the potential for white mold infection, and this goes for kidneys and other edibles too. Where we have the cooler, wetter soils, we tend to drop our populations there, reducing our inputs, reducing our liabilities in those high-risk environments. And we've gone down on soybeans, we've been down to 60,000 in those cooler, wetter soil environments and not seen any negative consequence to yield. And that's regardless of a white mold year or not. Variable rate pesticides, like I just gave the example with the Contans, where we know that we've got the inoculum in only this 1/3 part of the field, and we've only got the environment in that same part of the field. Just treat that one part of the field with that high dollar input. There's potential for variable rating fumigants ahead of potatoes as well. I see that I've got a little bit of time here. This is just another example of where we've taken the zone modeling, the zone soil sampling, what we understand about nutrient use efficiency and marketable yield potential to create more accurate variable rate prescriptions for inputs. In this case, it's potash going ahead of a potato crop. So on the top right is our zone map, with the red zones being our drier soils, where we have worse nutrient use efficiency. But if you look at the bulking and yield curves below that, you'll see that those red zones, which is that red line, that's actually some of our highest yield potential in this type of production environment. So we've got low soil fertility, poor nutrient use efficiency, high yield potential. Those are all important factors for creating an accurate variable rate prescription for potash. And we can similarly manage our other inputs like nitrogen, irrigation, water, and fungicides. I see that I'm coming close to time here, so I guess I'll open it up to any questions. I don't want to pick on anybody, but Jim Bridges, you promised you'd have questions.
You answered all my questions.
All right, well done.
Hey, Michael, do you do any variable rate 2x2 on the planter?
I have not. There's opportunity to do it, but I don't have anybody that's really interested enough in doing it at this point. Like I said, most guys, when they get started on variable rate, it's usually on the seeding side. And with the high resolution soil mapping that we do, variable rate seeding, variable rate anhydrous, and variable rate irrigation, if you have emitter level control, are the best ways that you can actually match up with the amount of detail that we're getting out of this process. Where you've got a spreader with an 80-foot pattern, there's not a lot that you can catch up with on some of these more variable soil types. But yeah, 2x2 would be a great way to actually match that. Mr. Martindale.
When do you actually install the monitoring, or what are the environmental conditions generally when you take the moisture readings?
So those were just to quantify soil moisture, map it, and compare it to what we had predicted for the relative changes in soil moisture, and that can be done at any time. Yeah, so I just did that at the time that we were pulling soil samples for fertility analysis. Yes, fall. I have done some high density grids with soil moisture mapping as well, and I've done that in the spring and summer. I don't recommend doing it in the summer in standing corn. not as fun to move through, but I wanted to see exactly how the spatial patterns changed following dry conditions, and then again after actually getting some significant rainfall. And the relative changes were very similar across both of those scenarios. So it gives us confidence in that we're actually able to map soil moisture variability, at least in relative terms, across these fields. Yes, sir.
Anybody that you know tried with micronutrient foliar feeding when with mapping, say take the samples to the trees?
So the question is if anybody's tried doing variable rate micronutrient foliar applications. I don't have any experience with that. I do see that I could see that working out in certain scenarios, but no, I haven't. Yes.
What systems do you work with, and do you write the prescriptions and load them and that kind of stuff?
Yeah, that's right. So we work with several different systems to create variable rate prescriptions depending on the types of controllers and what inputs we're working with. But yeah, that's something that we do pretty much from start to finish. We do the mapping, we do the recommendations, we write the prescriptions and help them get uploaded into the right controllers in the right format. Yeah.
Doing your mapping and stuff, do you actually have to have boots on the ground, or is it all imagery, or using PC or anything like that? Or is it all imagery?
Yeah, so the question is what layers inform our management zone model? And we can pull from all kinds of different types of data, all kinds of different types of maps. The specific maps that we use are heavily dependent on the soils and climate that we're working in. So typically we don't use a lot of electrical conductivity mapping, but where we have soils where soil salinity is something that we're really concerned with, that's a great application for electrical conductivity or EM mapping. Most of the soils that we're working with, especially where we have bare soil imagery, we're measuring changes in soil brightness and soil color, mapping those out and combining that with surface flow modeling and sometimes yield or historic plant health mapping to create a management zone map that reflects the variables that we're trying to manage in that environment.
Mike, we've got a question online. And Nathan Brearley was asking, have you done any testing behind like the curse buster?
Have we done any, what type of testing behind the curse buster? Okay, I have not done any type of testing behind the curse buster. Jim, do you have any? No. No, so that would be, I guess, something to put into our trial design for next year is to get the curse buster out there and do a side-by-side and see if there's any differences in soil moisture, soil biology, soil chemistry. Right. Yeah. So in those management zones, those examples that I gave earlier, where we have those highly erodible soils, there is potential then for variable rate tillage, where you have automated depth control. So you could potentially create a variable rate tillage map based on this type of management zone. I know people out there are doing it, but we don't have anybody that we specifically work with that's taken it to that level yet. But this would be a good environment to try something like that on these highly erodible red and orange zones. Paul, do you want to introduce the next speaker? Thank you.
Thanks, Mike. Yeah, I have to say, when we go behind these zones for soil sampling, it really makes a lot of sense when you're in the field, the lay of the land and the color of the soil. So it's been really working good for us. So our next speaker before lunch is Dr. Jerry Hatfield. Jerry Hatfield is a previous laboratory director and supervisory plant physiologist at the USDA ARS National Laboratory for Agriculture. I think he retired in 2020. Jerry received his BS in 1971 from Kansas State University, his master's in agronomy in 1972 from the University of Kentucky, and received his PhD in 1975 from Iowa State University in agricultural climatology. But more than that, I think that's not as important to Jerry. He's very passionate about agriculture. He's passionate about soils and conservation, and so we're super excited to have him take time out of his week this week to be with us. So welcome, Dr. Jerry Hatfield.
No, soil health, Lake Mills.
Just remember to repeat the question.
Yep. Yeah, remind me when I forget that.
All right. Thanks, Mike, for that really excellent introduction into spatial variation and why it's critical in all of this. And I do want to talk today about soil health and what it means for oxygen, water, and nutrient availability, because we often don't think about those things that way, and productivity. And thanks, Paul, for the invitation and everything. And we're going to breeze through a lot of material in a short period of time. But at the end that you'll see my email address. So if you want these slides, feel free to request them. I'd be glad to give them to you. You can use them wherever you want and everything. So, and sometimes you just need to sit and think about it for a day, 2 days, 2 weeks, things like that. So I'll be glad to have a conversation with you about that. So what is soil health? I mean, that's probably the biggest question today and everything else. And people are scrambling to find a perfect measure of soil health. But it really is about the ability of the soil to provide these critical functions: supplying water, supplying nutrients, supplying oxygen, and providing support. We want that plant to have adequate water. We want it to have the nutrient needs. It needs to have an aerobic system within the environment, and it needs to stand up. And you think about all these different things, and the Food and Ag Organization lists 14 different functions of soil out there. But the one that they don't ever talk about is the gas piece of it. They really, in all of these different dynamics, it's really, that's kind of an afterthought and not even a thought at all. So I'm going to start you off with questions today. This is audience participation time. So I get to ask the questions before you get to ask the questions at the end of this. So what's the most limiting factor in crop production? Carbon dioxide? Water. Anybody else have a different one? It's probably water. We have plenty of CO2, as all the climate people will tell you, that we overabundance of that piece of the puzzle. So, you know, water is probably one of our most limiting factors in crop production. But then now you ask the question, what's the most second limiting factor? Fertility, sunlight, anything else? Time. Length of the growing season. Number 2 is a mishmash of stuff. I mean, you really begin to think about it. But then you really need to ask yourself, what do you really want from your crop production systems? You want yield? You want profitability? You want quality? All these things. Do you really ask yourself that question at times of saying, what do you want out of your crop production system? I think these become important questions. This journey down soil health, where I find the most confusing, is that everybody wants soil health. But when I ask them is, what ends do you want? Then we start getting a lot of blank stares. I don't know why I want that. Everybody tells me I should have it. Well, why do you need that piece of the puzzle in terms of how do you think about this? And then the more important question is, how do you go about enhancing that crop production system out there? Michael just gave you lots of different technologies. And I'll end the talk this way of saying, what we really need in agriculture is more innovation and more creativity. And I think you just saw an example of how we can now take technology and begin to put it into innovation that leads to more creative crop management in all of this. So the real question is, how do you go about enhancing that overall system? How do you really go about doing this? I built this slide a long time ago before soil healthy really became a buzzword. And I called it the soil aggradation climb. We always talk about the soil degradation spiral, but now I've put it in reverse order. Because if you take a look at how we change soils out there and think about it as a ladder or a stair step out there, the first rung on that ladder is biological activity. We don't change soil without changing the biology. And once you change the biology, then we see organic matter turnover, we see nutrient cycling going on. Those things we really don't see within the soil. They're sort of like microbes. You know, we know they're out there, but we can't really see them. We don't see a lot of these invisible and dynamic processes, but we do see the visible outcomes. We see the visible outcomes of renewed soil structure. We see improved water availability. We see all these different things that we can see of this. But to change that biology requires 4 things. It wants food, water, air, and shelter. It wants to be fed, wants to have a drink, needs air. Remember, I didn't say oxygen. It needs air because if you really think about what air consists of, 78% oxygen, nitrogen, 22% oxygen, and 400 parts per million CO2 in all of this, is that a lot of our microbial systems rely on that nitrogen gas that's in that soil air to function as well. And then we need shelter. And shelter is very simply is, don't keep disturbing me all the time. Let me have some peace in terms of all these different puzzles that are going on. Here's an interesting piece of this dynamic that's going on. This is a study that was done by Wishmeyer and his colleagues. They went through and surveyed all the literature around the world and said, what were the most important factors that caused soil organic carbon to change within the soil? Looking across all the different literature that had been written. And the number one thing that popped out was microorganisms and fauna. Is that we need to change the microorganism structure, that those are the driving processes of how organic matter and how organic carbon begins to change within the soil. The next one was clay content or texture, because that's really a lot of the space in which we see a lot of the nutrients stored away. Land use and management. Then we got into the type of vegetation that was out there, climate, topography, parent material, and then finally, physics and chemistry. If you go to most soil science groups and everything else, physics and chemistry are what drives organic matter changes. but actually they are a distant piece of this overall puzzle. We've got to get the biology right, and everything else will fall into place. And so it really becomes a biological system. And how do we begin to look at this? Your trivia for the day is that underneath a really healthy biological soil out there, there's the equivalent of 2 African elephants per acre. Anybody know what an African elephant weighs, a mature African elephant? Yeah, anywhere from 3,000 to 5,000 pounds. 10,000 pounds of biological material below every acre out there. If you had to feed 2 African elephants every day, how much do you have to feed them? Anybody know? African elephant eats somewhere between 200 to 500 pounds a day. You know, it takes a lot to keep 5,000 pounds fed. You got to think that same way in terms of the soil as what's it take to feed 10,000 pounds of soil biology out there. And that's really what we're going to focus on as we go through this. So now we know that microorganisms are important. The real question is, how do we feed those microorganisms out there to keep that soil healthy and going on? So we're going to start off in terms really the carbon energy flow path. How do we take and begin to look at this? Paul kind of set this up very nicely for me, is that in reality, what we have at the beginning of this whole process is sunlight. We take that sunlight through the photosynthetic process. We take CO2 and we take water vapor. We make it into a simple sugar. We take that simple sugar and we move it down through the plant stem, through the plant roots. We exude it out. That feeds the microbes. That feeds the soil fauna because of all the biological activity that's going on. Part of that goes to nutrient cycling. Part of that goes to carbon cycling. You get all these different pieces come back that use to produce the food, fiber, and fuel that we want. And then we take CO2 back out of that, and we begin to put it back through the overall process. Nature is a very dynamic and very sophisticated system. It is far from simple. But if you look at this overall process, because in reality, what we're talking about is how do we capture that energy and make it available to change that soil that's out there. It really is that process that's going on. And if you take this system and begin to spread it over the whole year, and you look at the seasonal input of energy, because we don't often talk about energy from this perspective. We talk about energy in terms of fuel we put in and energy in terms of fertilizer, but we don't think about energy relative to that plant very well. And you look at that yellow area, that's the sunlight that comes in and how it grows that plant. We put that into the soil. The red piece is how we take it back out in terms of microbial activity and everything else. But I want to dispel one piece of falsehood in all of this, is that everybody thinks that if we have microbial activity in the soil, which is breathing and it's taking in oxygen and it's giving off CO2, that those microbes are contributing to all the problems we have with climate. No. The reality is that that CO2 that comes out of the soil in an actively growing crop never makes it to the top of the crop canopy. It is absorbed that efficiently. We've seen that, we've measured it over time and time again because we have multiple profiles of CO2 within the crop canopy, is that we can, and during the middle of the day, we might have a CO2 level that's 600 to 700 parts per million at that soil surface. Never makes it past the ear leaf. It is now taken out of that atmosphere so quickly in all of this. So that CO2 that's coming out of an actively growing soil is basically CO2 fertilization of that crop. And so you see that different piece of the puzzle. We're not contributing to climate change. We're basically recycling and putting it back into sugar that goes back into the soil. And so you look at all these different dynamics. Here's just an example of this. That black line across the top is what's at the top of the atmosphere. This is Ames, Iowa. That yellow line across that is just 1 year of data. You see all the variation that's going on. The green arrow on the bottom part is what's captured by that crop. We can actually measure how much CO2 or light was captured by that crop. how much energy was going in there. That blue line is what I estimated going out of the root into the soil in terms of the exudates expressed as calories. You have to look at this during the middle of the day in an actively growing corn crop. We could be pumping anywhere from 50 to 100,000 calories per square yard, or basically per square meter, every day back into that soil. And you say, man, that's a lot of energy. You take that 10,000 pounds of biological activity, 50,000 calories per square yard is nothing in terms of being able to provide that energy source for them. We need to start looking at it from an energy perspective. Because if you want that biology to grow, you've got to begin to feed it. Because what happens when you have excess calories? Everybody just come off of Christmas season and things like this. How many people had excess calories in their life? Yeah, go ahead, raise your hands. Those that didn't raise your hands, I know you're lying. So, you know, if we have excess calories, what happens? We gain weight, right? We wear it. We adjust our belts. No, all of this in terms of the overall process. And so we need to start thinking that way about soils. If we want soils to change, we now have got to supply that excess energy to make it happen. But all you look at this in terms of this overall process, this is just a very complex diagram from a couple Russian authors that we found that actually spent a whole article talking about the role of sugars in the system. It's the first time that we've ever seen anybody really talk about it from that perspective. And I want you to pay attention to not this complex diagram in the center, but that time scale on the bottom. Because what we see when we see that root exudate, and Paul showed that wonderful example of roots throwing off exudates in there and all of this, is that we see a microbial response within seconds. And we've seen this in the laboratory when we begin to push that whole system and begin to add those sugars back into that. We see an increase in CO2 bursts coming out within a matter of 20 seconds in all of this. This process is going on very, very quickly. And then you finally see that here's organic matter changes out, which is in the order of years. But there are a lot of things that go on between seconds and years out there that I'll explain as we go on. And you see all these different pieces that are coming together. And it's all driven by the biological system that's working for us. And if you look at this, Paul talked about 20% coming in. There's actually people that found that maybe 40% of that photosynthetic carbon is exuded from the roots. And you see this. Glucose is the most abundant one of those. We get fructose, saccharose, ribose, all these different things. Basically, most of that carbon that's coming out of sugars goes back as CO2. Remember, I said it didn't really go out anywhere at all. And about 2 to 5% finally ends up in some form of organic matter. But in between, there's a lot of things that happen within that soil. Also, what we find is that a lot of this is about that root system. And if you really look at what we do to manage that root system, how do we cultivate, not in a tillage sense, but how do we cultivate an actively growing biological root system out there? Is keeping that root system in place, allowing it to do its thing, because that's where a lot of this material that's digested very quickly, the biology is coming from. It's not coming from the residue on top of the surface, it's coming from that root system that's down below. So if we want soils to change, we've got to supply the energy that supports the biological activity. It's really pretty simple. Energy in, biological activity out the other side. And we see the changes in all of this. The other piece of this puzzle that I'll dispel a myth on is that everybody says, well, you know, it takes years and years to see this change out there. This is a study that we did a few years ago. We took a conventional tilled field, and you'll see some of the impacts of conventional tillage in this. We converted that field, it's 320 acre field. We converted it from a conventional till system to a no-till with cover crop. We did a sampling across this field. When we made that transition, we sampled every 150 feet down to on a grid by 150 by 150 by a depth of 4 feet, and every one of those gets added into 6-inch cores down there. We measured the microbial biomass at the beginning, then we sampled again in the fall of 2017. After 1 year of no-till and 1 year of a cover crop, we doubled the microbial biomass in the upper 6 inches. People said, you can't have that. No, biology does respond quickly. We've seen that in controlled studies. We've seen it in field studies that the biology, if you feed it and you keep it sheltered, it responds very, very quickly in all of this. These same Russian authors found this relationship between soil organic matter and a lot of different things. There's sugar content. I would have plotted the graphs differently, but Russians don't always express things the way we do. Is that the higher the sugar content, the higher the soil organic matter content within that. We see differences among soils. We see differences among cropping systems, management systems. But it really is driven by how much sugar we put into that soil and how much that biological activity that's above the surface is contributing to what's below the surface. So we see short-term and long-term impacts. Short-term, and we're talking about less than a year on short-term. Increased microbial biomass, soil aggregates. We've seen changes in soil aggregate structure within 140 days under controlled conditions. We see improved nutrient cycling. We see a lot of these different things going on. We see improved infiltration, and I'll talk about that. We see improved gas exchange in all of this. Long-term, what do we see? Improved nutrient cycling and availability, because that biology is working all these different processes going on. That's why clay becomes so important, because of all the intercellular spaces within clays in which things are tucked away. And microbes go get that and begin to release it. We see decreased field variation. I'll show you that example as we go along. We see stabilized yield variation among years. We no longer see this big response to the weather because we got all these different pieces, and we see increased profitability and production efficiency of our natural resources. This is in that 2 to 5 year change. So if people tell you that it takes decades to change this, tell them to come talk to me, because it doesn't take decades. The other piece of this puzzle, in addition to soil health, is regenerative agriculture, and that's become the new buzzword of the day in all of this. And in reality, if you look at the principles of regenerative agriculture, it's really kind of common sense sort of things. It's common sense of saying, how do I maintain my crop residue to protect that soil surface? How do I minimize the soil disturbance in terms of reducing the intensity of tillage? It doesn't say reducing all tillage, it says reducing the intensity of that tillage. How do I maintain that continual living plant root, which is nothing more than how do I maintain a continual input of energy into that system? And how do I add diversity? Because diversity on top is diversity below. Diversity on top is a slight change in the quantity and quality of the exudates coming out. There are a lot of different things going there. And the final piece of this is this integration of livestock. How do we begin to utilize livestock as part of the system? Because now we're talking about getting the carbon and nutrients together in a form in which we can have a positive benefit on soils. See, all these different things that are coming together. And so we have to understand why these principles put together. So now I have another series of questions for you. What changes first in the soil? Anybody want to guess? Aggregation? Anybody else? What's that? Moisture. Actually, water, you're right. Water changes first, because if we look at the dynamics of soil change, we'll bring this together, is that we have water dynamics, then we have carbon dynamics, and then we have nutrient dynamics. These are the blocks that occur, because one of the things we affect first is the water dynamic. And if you look at what really happens out there in terms of this maintaining soil armor that's out there, that residue across the surface, is it shows 3 advantages for soil water. And these are immediate. Put that crop residue layer out there, what do we see? We protect it against raindrop energy, so the raindrop energy is no longer hitting the soil surface directly, it hits that crop residue, it moves slowly through that crop residue, infiltrates in that because we can maintain infiltration rates. Anybody want to know what the average infiltration rate of Midwestern soils are? Take a guess. 1 inch per hour? What? Cut Paul's number in half. A ½ inch per hour is a lot of cases what we see across the Midwest. Sometimes we can get up to that inch an hour. 2 inches, we've got a lot of rain. If it rains an inch an hour and your infiltration is a ½ inch hour, what happens to that other ½ inch? It's gone. It's not how much rain you get in the rain gauge, it's how much rain you get in the soil. And we need to start thinking that way because somebody mentioned the fact that we really are about moisture management. Michael mentioned it, that moisture management is critical. And in fact, water management is going to be our biggest challenge as we go forward. How do we manage the water that we have because of the variable rainfall we have? How do we match it with the cropping systems? How do we look at it with soil health? The second piece of this puzzle in terms of now getting water into the soil is that residue layer reduces the evaporation rate. So what happens is that water gets down through that residue and it now wets that soil out there, is that we no longer have input of energy in that to evaporate the water. And so we reduce the evaporation rate by about 80%, which means that we keep that soil moisture near the surface, we keep it cooler near the surface, and what that ends up doing is creating an environment in which those plant roots are very, very near the surface. In digging a lot of plant roots and everything, we find that underneath the residue, as those roots may be within 2 inches of that soil surface. 2 inches of that soil surface, highly biological activity, a lot of nutrient availability, a lot of water availability, take advantage of light rainstorms, but all these other things, plus the fact that that's where most of the oxygen dynamics are occurring as well. So we got a very active biological system out there, and all we did was change the residue across the top surface. Whether it's living or dead, we see that same impact. We also influence the microclimate that's in there because that continual soil cover reduces temperature extremes. And it maintains the temperature in the optimum range for microbial or biological activity. We did a little study along the way because we got very curious about this. And we looked at surface temperatures under conventional tillage systems. 6 years of my career was spent in Lubbock, Texas, on the high plains. Skip row cotton and everything else, we'd spent a lot of work looking at how crops use water in that semi-arid environment of 16 inches rainfall. We could have soil surface temperatures between those rows of cotton that were in excess of 150 degrees Fahrenheit. You cannot walk across that barefooted. And what you find is that that extreme environment produces a lot of stress. All you had to do to reduce the stress in that environment was go away from skip row cotton to go equidistant cropping space, and we changed the whole microclimate. But we got very curious about the overall climate in the Midwest as well. And so we measured soil surface temperatures and we measured temperatures at 1 inch under this. And this is just the number of hours in which that soil was above 40 degrees centigrade or 104 degrees Fahrenheit. Because 104 degrees Fahrenheit is when you begin to denature protein. You basically destroy that microbe that's out there. And you see the number of hours, and they change by how wet that soil is during the spring. But what you don't see is what the soil temperatures were a number of hours above 104 if you had a residue layer out there. They're actually plotted on this graph, but they're all zero. We never got that hot. We always were below 90 degrees, and typically we're at 85, 86 degrees, which is optimum temperature of biological activity. Nature does know what it's doing. If we quit trying to mess with Mother Nature, we'd be better off. And you look at all these different dynamics going on. This is just an example of all these different things. We talk about a soil that has low biological activity. You may go out there and look at it and say, yeah, that's got some aggregates out there. It seems to be a little bit piece of this. As soon as that aggregate is getting hit by a raindrop, it begins to dissolve into sand, silt, and clay. What happens when that silt moves through the profile? It clogs up all the pores. Once we clog up all the pores, infiltration rate goes away, and that's when runoff begins. But if we've got a high biological activity soil, plus protecting it, all that, is that we maintain our infiltration rates. It's not uncommon for producers to come up to me that have been in long-term regenerative systems and saying, yeah, NRCS came out and we measured infiltration rates and they are 10 to 12 inches per hour. So what I want to do is start an infiltration contest. What system can give me the highest infiltration rates that's out there? I'll have to set the guidelines for it so you don't cheat. But in reality, people are seeing that they can capture all of that rainfall and make it available to that crop, because we do have some tremendous impact on infiltration rates. And we have tremendous impact on gas exchange rates as well. And so you see all these different pieces that are going on become very important in all of this. But if you just think about it very simply in terms of cover crops, they say, well, what do the cover crops do? You just think about it from this system and everything else. That little green bar on the left side is what we've got in our traditional systems, but we just add that cover crop system out there. Is we just extend the time in which we're capturing energy. And so I did a little analysis and said, you know, how much solar radiation is available in what I call the shoulder periods? Maturity of corn to the first frost, last frost until we really emerge that corn plant out there. And what I found is that about 25% of the total yearly solar radiation in Ames, Iowa was available in those, what I call the shoulder periods. But 25% of the total solar radiation for Ames is a lot of sunlight to grow a plant. That's a lot of sugar that we can make. And so we need to think about not a cover crop, but we need to think about extending our ability to capture sunlight to make sugars to feed the microbes. Because we know the microbes are still working at those temperatures as well. They don't shut down when corn reaches a maturity. They don't shut down until corn starts to grow. They're working all the time, and so they need to be fed if we want to keep them really going. And if you think about it this way in terms of looking at what that changes in terms of organic matter, is I put a lot of stuff on this one slide for you, is that we know that soil water holding capacity changes by the texture that's out there. That white bar in between, or the white area, is available water between wilting point and field capacity and all of this, and it varies by the type of soil that's out there. Hudson, and former SCS employee, or NRCS, found that when we went through the whole soil survey database, is that the more organic matter we had, the higher the water holding capacity, the difference between the upper bound and lower bound. And so I took that. I said, so what is this water worth to me? And so that lower graph is I just took a silt loam soil, computed how much a crop uses in terms of corn crop uses in mid-August across Iowa, and said, you know, if we had 2% organic matter, 5-foot profile of exploring all of that, that we'd have about 8 days of available water in that profile. But if I went to 4% organic matter, it was 13 days. So I had 5 more days of available water in which that crop wasn't stressed. What's 5 days in which that crop isn't stressed in the middle of August worth? Money, right? That's where profitability comes from. Not having that crop stressed during the grain filling period in terms of this overall puzzle. And if you look at it this way, what we see in terms of the organic matter changes is we don't change that wilting point much, but we change the capacity of that soil to hold water. 1% organic matter is worth about 8% water availability. So you see this big change in there. So if we decrease that, we decrease the size of that box that's out there. But if we increase it, we increase the size of that box. So we can change all of this. So it becomes a matter of how do we begin to look at the system in terms of these overall dynamics that are going on. But here's the sad truth. These are the data from the Morrill plots in Illinois and the Sanborn plots in Missouri. Long-term studies, you go back, you see that 1880s and when a lot of those were started, they've had the same crop rotations, all these different periods of time. The lower one is the Sanborn plots. Just pay attention to the continuous corn line, which is the bottom one on the Sanborn and the bottom one in the Morrill plots, is that we've lost about 70%, and that was by 1960 in terms of the continuous corn and the Sanborn plot. 70% of the original organic matter was gone. And the Morrill plot's about 60%. Across Iowa, we just did an estimate in the last few weeks. And we've probably lost 60 to 70% of our original organic matter across the soils of Iowa. Pretty scary, isn't it? You think about what we've done to our overall agricultural systems. And people come up to me and say, well, how do yields keep increasing? We try to outguess Mother Nature. Why do we see all that field variation that's going on that Michael talked about? We see the field variation because we took that organic matter out. Those knobs in the central part of Iowa in 1970 compared to what they were in 2020, those knobs in that Clarion Canisteo soil are about 3 times bigger today than they were in the 70s. We've eroded that much organic matter back out. You begin to see that piece. Mark?
Because of the CO2's carbon and stuff and plowing and
Plowing, erosion.
so you lost the elements of life.
Yep.
Carbon there.
Yep, we've stripped the carbon out. We've taken it out. And it's really, we've increased our field variation.
Wheat right there and stuff, you look at corn way at the bottom, you think about the Great Plains and stuff, and the whole Dust Bowl and everything was all caused just because of strength and soil and that.
Yeah, we created our own problem at times.
So it wasn't the plows, actually, it's carbon.
Yeah, it's carbon loss. I mean, anytime that we reduce the carbon, you see that same thing in terms of the aggregation process, is that we now make that soil fragile. Bare soil, lack of carbon, sand, silt, and clay, wind hits it, it blows. All these different pieces. This really intensive tillage, Don Rakowski has done a lot of work out of Morris, Minnesota on this, in terms of looking at CO2 bursts coming out, that initial primary tillage, breaking that soil into big chunks in all of this. Big massive CO2 loss in terms of these overall dynamics. We've done other things in which we actually have very sophisticated instruments. This is an eddy flux thing that allows you to measure the CO2 and water vapor in the atmosphere. This is mounted over a corn soybean system. A typical corn soybean production system under conventional tillage loses about 1,000 pounds of carbon per acre per year. Pretty scary when you think about that. Farm 40 years, you've lost 20 tons of carbon out of that soil. Everybody says, well, you know, that's all flux measurements and everything else, but what the soil measurements tell you. So we actually did that. We know exactly what that eddy flux measures out there, and then we actually did the soil sampling. That's those black dots that are out there. We did measurements between 2006 and 2016. We have to have that period of time. You can see that the numbers are exactly the same. What we saw lost in carbon is what we estimated coming out of the whole carbon budget across that. We can do pretty well in terms of saying our soils are changing, what direction are they going, all these different pieces that are out there. Marty L. Casey did another study across different parts of Iowa. This is no-till, strip-till, conventional plow, or chisel plow, deep rip, and moldboard plow. You can see that no-till and strip-till were accruing carbon, and the chisel plow, deep rip, and moldboard plow were losing carbon, and across all the different sites that are going on. So what we've done in our agricultural systems is we've changed our soils. We've reduced our organic matter through really intensive tillage out there. We have cropping practices that limit our return of carbon into the soil. Short season crops, a lot of that available soil radiation we're not putting back into green material, which means that we've reduced the functionality of our soils. We've increased our reliance on external inputs. We've increased our erosion rates, and we've increased soil degradation. Our erosion rates across the Midwest are actually increasing rather than decreasing. Our soils are becoming that much more fragile. So the other question for you to consider is, so if we restore our soils, what will happen? What would happen to the Midwest if we restore our soils? More water intake? What else? Lower carbon levels. The whole premise of carbon markets is that we're going to use carbon or soils to store carbon. Let me tell you, if you want to get into storing carbon in your soil, do it for yourself, not for the carbon market. I'll show you that as we go along.
What's alfalfa do in the rotation with the carbon levels?
Okay, what's alfalfa do in rotation in the carbon levels? Anybody want to answer that question? No, I'll answer it. Deep-rooted crop, but we're taking that crop off every 30 days, every 35 days. We're doing a lot of that carbon up to regenerate that plant that's out there. Even though we have a deep-rooted system, we may not be adding much carbon back in because of all the energy it takes to keep regrowing that crop. You think about the overall carbon balance that's out there. We do remove a lot of water out of that profile. I grew up on an alfalfa, sorghum, wheat rotation system and everything. We had to be very careful after we took alfalfa out of the 5 years because that soil profile was so dry that we had to put sorghum into that to have a drought-tolerant crop. Put wheat into it, we'd generally have a crop failure. So you think about all these different pieces that come together, we need to understand the system and understand the dynamics of what's happening with crop. So if you look at this process of change out there, is that it really begins by how we change the water balance, that changes the carbon balance, that changes the nitrogen balance. The unfortunate part is that we do not understand these interactions between water and carbon, water, carbon, and nitrogen, or even carbon and nitrogen very well yet. We need to understand these to really crack a lot of this understanding about how do we go back to the alfalfa question, saying what does alfalfa do in this system as well. But if you look at this just from a soil water, soil carbon piece in all of this, if we increase the soil water, we decrease plant stress. Once you decrease plant stress, you increase plant growth. Once we increase plant growth, we increase the carbon input into the soil. Once we increase the carbon input into the soil, we increase water storage. So that increases the soil water, we go around again. But as we increase the carbon input into the soil, we increase the microbial activity and nutrient cycling that then further increases plant growth. And so you see this very simple diagram says that this unlocks some of our understanding about how do we begin to change the system. We could do another one if we say, all right, so now we increase the oxygen content, and what does that happen as well as we go through this? Because soil water is so critical to this, because we find that a lot of our yield reduction is really due to short-term water stresses. It's not the drought. Drought does cause lots of problems, but a lot of these yield losses are caused by short-term water stress. Short-term water stress is like this. Crop uses about a half inch of water, or corn uses about a half inch of water per day during the maximum grain filling period. Means that over a 7-day period, it could use about 3 to 3.5 inches of water. We've got a soil profile that only holds about 10 inches of water, and we need to replenish that. But we need 3.5, but it only rains 2 inches that week. So we got a little short-term stress. We see it in terms of the flux measurements of CO2. We don't see it in terms of the physiology of the plant of curling up. So we said, well, it's really not stressed. Yeah, it was stressed photosynthetically. It wasn't visually. And we see all these different dynamics that are going on. It's a yield and profit robber that we really don't characterize very well. I want to take you through a case study in all of this. This is from Wayne Fredericks. Wayne and I have spent a lot of time working together. He farmed up in Mitchell County. He spent 19 years as a conventional producer. He switched over to no-till soybeans in 1992 because of this. It froze quickly in the fall of 1992. He couldn't get his fall tillage done, and so he decided to go to no-till beans the next spring. Worked so well, never changed back. Finally began to look and say, you know, no-till beans are working for me so well. What if I go to strip-till corn as part of the system to push my fertilizer a lot more efficiently, particularly the P and K and all of this, and then begin to experiment with cover crops in 2012. This is just what his fields kind of look like in the spring. The lower left one is he now plants green with his cover crop and everything else. But here's the data set. So I asked Wayne, we often appear on different speaking engagements together. I said, Wayne, you talk about all the different things that occurred within your field. Would you be willing to share all the data that you have across your fields? He said, what do you want to do with it? I said, I want to analyze this for the types of changes that have occurred. So he gave us all the data. He had soil organic matter samples. We had yield monitor data across that. We had weather data from Mitchell County. We had the Mitchell County crop yield data. He had his data as well. We looked at organic matter changes. We looked at field versus county level yields, field uniformity of yield, and weather resilience, and all of this. So a number of different things. We're talking about yield monitor data from 2002, an initial data set through 2018. We added to 4 more years through 22 as well. And so it took a year to analyze all of these data because we took the yield monitor data and we segregated it by soil type within the field. Just mask it to that level so we could look at the changes within the soil. Here's the organic matter changes that are going on. This is a switch between the no-till and strip-till. This is 1984 all the way through 2015. We've actually done some sampling since then. Been a 2.5% increase over the 25 years. We actually sampled fence rows to see what the potential was in terms of what we could store up as well, because you get to 6.1 and say, well, how much more can I get there? That field you could actually probably go to about 9. That's what the fence row was around next to it. But if you look at this, in our agriculture, and you go back to those long-term plots of Morel and Sanborn, we've extracted a lot of organic matter out of that and everything else. But if you put it into that regenerative system, is that we do see these organic matter changes over time. But here became the more fascinating part to me, is that in taking that yield monitor data and looking at it, and just 2 different soils within this, and we see the same thing on field average as well, is that as we went from 2004 to 2018 in that Ostrander loam, is that we took out all the low yielding parts of that soil. And we also made it much tighter about the mean. So we're making that field more uniform. Anytime that you take out that left part of that rotation or that distribution is profitability. And we see that over across all the different soils. We see this change over time, is that we're making our fields much more uniform in terms of the things that we're doing out there. And you see all these different pieces that are occurring. The other thing we saw an increase in water use efficiency because we were making more use of every drop of water that fell during the summer. And the way in which we do this analysis, it takes all the different variation of hybrids and changes in maturities across all the different years out of the system. But the more important part and fascinating part to me is that when we started looking at Mitchell County, and we've looked across the Midwest, is we see 2 important pieces going on. The more it rains in April and May, the lower the average county yield. Pretty simple. We would delay planting rates. We have a lot of flooded out areas in the fields, things like that, that really reduce our overall county yield. Conversely, the more it rains in July and August, the higher the average county yield. Pretty simple. It's the maximum area of the growing season in which crops need water. The more water we supply, less stress, higher yields. When we begin to look at the overall fields that we had out there in Wayne's data, is that we no longer saw that correlation. We were able to plant on time because we could traffic. We was having that gas exchange within the soil, so we weren't seeing that effect of flooded soils. All these different things that were going on. So we see these correlations go away. We also see that even though we didn't change nitrogen rates, we were increasing yields all the time, so we're becoming more nitrogen use efficient. A little bit because of water, a little bit because we actually had better soils. So I ask you one question. What's your goal in your cropping systems out there? What's our goal in agriculture? And I'll just introduce you to this concept, what I call genetics by environment by management, G by E by M. Well, geneticists always talk about G by E, but I decided to add one more term just to confuse everybody on this. So you think about it this way. Is genetics by environment by management? Is what do you control? You control the management piece, and you control the genetics piece. Do you control the environment piece? Not very well. You've got to farm the soils that you got, and you have to cope with the weather that occurs. And so if you look at G by E by M, is think about it this way. Is management is what you control and what you do to optimize the genetics given the environment that you've got. And you start looking at that way as now it becomes a puzzle in which we begin to look at. And you have control over the management decisions. You have control over the management decisions that allows you to really begin to think about how do we optimize our system. We can change that soil environment in terms of improving the variation that's going on within the soil type. And we can really begin to capture more of that potential of that genetics that's out there. So we've got soil management practices, we've got water management, we got pest and pathogen management, time of planting, cover crops, crop rotations, erosion conservation, nutrient management. All of those things are your management decisions. But now start looking and saying, what do those management decisions do to my soil resource and their ability to cope with the weather that's occurring during the growing season? And then it's reflected back in the genetics that are out there. Are you really getting the maximum return on the genetics that you want to or are capable of with the system that you got out there? Because you go back to these principles of regenerative agriculture, keeping that residue out there, reducing the intensity of tillage, keeping that continuous energy going into that system, thinking about diversity from an entirely different perspective that's out there, and integrating livestock into that system. And this integration of livestock doesn't necessarily mean hooves on the ground or feet on the ground. It means how do I utilize, now I call it bio-based nutrients. It sells a lot better to that consumer community if I don't call it manure. But if I call it bio-based nutrients, everybody says, man, that's really fascinating. Yeah, it's just manure and a different name. But, you really begin to think about it. How do we utilize that manure resource? Because it has a carbon-nitrogen ratio that's really critical for us. And it has carbon as an energy source. It has carbon in all of this. I'll just up you one on your maps, Michael. This is profitability maps in all of this, because I think now if you can take all the things that Michael talked about in terms of saying what's the variability out there, and you say, where are my profit zones in that field, and where are my non-profit zones? We need to start looking that way and saying, are we getting our maximum return out of the investment on all of our field to be able to do this? I'm going to leave you with these challenges. I think we need to start realizing that our agricultural production is a system that have overlapping and interacting cycles. Water, carbon, nitrogen are interacting and overlapping in time and space. But they operate within an ecological system. We need to start thinking much differently about the scales in which we're approaching this problem. But also, agricultural production is an adaptive management, continuous improvement process. Manufacturing has used this for a long time. Agriculture has done this for a long time, but never used these words. How many people do the same thing year after year after year? Maybe too many. But in reality, agriculture has always been adaptive management. We've made tweaks as we've gone along. They may be subtle, but we continue to evaluate the system. But I think we need to ratchet that up one piece. We need to ratchet it up one level and say, when we start looking at the technologies that we have available to us, the sensors, the satellites, all these other things that are going on, yield monitors, start stacking those up and saying, what are my fields and how are my fields responding? Then it'll open doors for us. And it'll open the last door out there saying that we have the potential knowledge. We have the technology. We can increase our production efficiency. We can increase our return on investment. But we need more innovation and we need more creativity. I think that's what agriculture really suffers today, is that we're not utilizing the innovation and creativity that the technology is laying at our footsteps. And I think that becomes our challenge. Because once we do that, I think we can unlock the potential of not only being able to improve our production efficiency, but improve the quality of what we produce as well. All of those things become very, very important to us. So now we'll entertain questions, and I'll leave this slide up so you can get my email address. I'll be glad to share these slides with you and all of this, or any of the other 100 decks that I have and all of these different processes that are going on. Here's my email address and here's my cell phone number. However, when you call my cell phone, it'll go to voicemail, because if I don't recognize your number, I don't really want to chat to you about Medicare, health insurance, of credit card fraud, or extended warranty on my car. So don't take it personal if I don't answer your call, but I will call you back or text you back on all these different ways. So that, I'll answer some questions for you. So, and I'll repeat the question. So it's all perfect. Oh, there you go.
So how much of this, when you talk about no stops and stuff, is actually a transportation of carbon versus loss of carbon? Like the hilltops that are, a lot of that I think is probably mechanical movement
Right.
versus actually loss.
Yeah, I'll repeat the question. How much of that loss is movement of carbon as opposed to loss of carbon? Do you think about these knobs that are out there, the light-colored spots and everything else? I'll give you one little anecdote on this, because a lot of that is movement of soil down there, because we do move a lot, and we've seen movement of soil down and erosion coming out of this. But what we do see, because we did an experiment, because with long-term monitoring, we have one of those flux towers that sets at 150 foot above the soil, or the above ground level, and it's actually on a hill west of Ames and everything else. It sees about 25 square miles in terms of its footprint. So after harvest, that CO2 level goes to about 400 parts per million. That's the typical atmospheric concentration, until all the tillage begins. And when the tillage begins, the concentration that we observe in the atmosphere is in excess of 600 parts per million, another 50% increase. And if you back calculate what it takes to increase the CO2 level in the atmosphere over a 25 square mile footprint, basically says that we took out all the carbon that we sequestered in those growing crops in a 2-week period and put it back into the atmosphere. So a lot of this we lose by how we manage that system out there. A lot of it we move by erosion. Some of it we move by wind erosion. I mean, if you look at all of this, you know, the Midwest, actually North Dakota, South Dakota invented the word snert. We saw that real time in Iowa this last year where we had that big blizzard in December. We had black snow along the edge of any field that had no residue on it. Yeah, we saw it in Indiana. Then we saw a few accidents in Illinois because of blowing dust and everything else across there. Erosion still remains our #1 water quality problem. Sediment going down the stream is still our #1 water quality problem. But we do have a combination. We send it back up by how we do this. We send it back out of how we manage this because we move that soil around the landscape. And I have people say, well, you know, I'm increasing the organic matter content in the low part of the soil, in the lower part of the landscape. That is rationalization for stupidity, in my opinion. I'll be quite blunt with you because I no longer have to work for USDA. I no longer have to be politically correct in what I say. And we have a lot of stupid decisions out there, and that's one of them in terms of this. So don't rationalize to me as saying, well, I've just increased the organic matter of the low parts of the field. Moving soil is non-productive soil. Think about it that way. If I'm moving it out, I'm not getting the productivity out of it. I've got to keep it in place to allow it to work. Other questions?
Do we have to add biology to the field, or is it there already?
Do we have to add biology to the field? Show of hands. How many people think they need to add biology to the field to make it work? How many people think that that's a bunch of nonsense? Nobody wants to commit themselves. Okay.
Well, the biology should be already there, as long as you have to keep feeding.
Okay.
Everybody's selling it.
Yeah, what do you want for the choice in the middle? No. Okay. Think about it this way. Long-term changes in soil. How many people have seen earthworms come back into their system? Where'd those earthworms come from? You know, I've had earthworm reports from central South Dakota, and I'm sure they didn't move all the way from central Iowa to central South Dakota, because that's a heck of a long trip for a worm. The biology exists within the soil. What we need to do is unleash its potential. What I get very fearful of is there are times that we may need to add some biology into the soil. But the real question is, what biology do we add? And I think that really becomes the critical part of the question. Do we add fungi? Do we add bacteria? If we add bacteria, which bacteria? We don't know anything about the soil microbiome. Let's be honest. And so to say, well, if we add this at 2 ounces an acre, you know, that's still a lot of microbes. But compared to what our potential is within the soil is saying, so if we feed that soil, getting more carbon, reducing the amount of CO2 that goes back out, all these other things, will we have a positive benefit? I'd much rather give it that try first and then see what happens. I think one of the pieces, and both Paul and Michael mentioned this in terms of trace genomics and what they're doing in terms of DNA and RNA analysis of the soil microbiome out there is giving us clues as to what the native resource is and how that resource is responding to management changes. I think it's technologies like that that will help us unlock some of this innovation and creativity. But there is a big market for biologicals. You know there's a big market because people are selling it. It's always a way you can tell. Now, whether it's effective or not, you know, we've seen some successes, we've seen lack of successes. But I don't think we understand enough about the system. But we do understand the general principles of how we have to look at it. Keeping that water, keeping it cool, allowing that biology to express itself, and boom, things will happen within that soil. So look at it that way first, and then figure out what's missing. Because you can tell me what's missing, you'll be a real genius. Because a lot of us are trying to figure that out, and we're scratching our heads all the time.
You think no-till is the answer?
Do I think no-till is the answer? Not necessarily. And I'll be honest with you. Remember, I did not say that when we talk about tillage in the regenerative principles, I said reducing the intensity of tillage. I think what may be very destructive is how we take 24-inch shanks, great big clods, moving them up, all these other things, and then we spend 3 operations trying to break the clods down and all of this. Full disclosure, I spent 8 years in California around the rice paddies and everything. Talk about an intensive operation because you take the flooded rice and then you go through and you run 24 to 36-inch rippers, create the big chunks, and then we ran big rollers across to mash those down, and then we cultivated again and again and again because we really didn't want infiltration at all. We just wanted it to be flooded. But you look at all this, is that we can manage the intensity of tillage to our advantage. And I think we need to look and say, how do we manage our tillage system to help us achieve our goals? And I'll come back to what are your goals for your system? Because there are times that maybe we need to do some tillage. But let's not get carried away with it in terms of this overall process. Yes, sir.
So you showed that data with the temperature of the soil.
Yep.
Especially rock and stuff. How have you seen increased residue both from reduction in tillage and cover crops help that? And does that also help the soil moisture? You know, this year, of course, the storm ground out here that these crops I think lived off of you for most of the season. Is that helping us absorb some more of that moisture, or am I just taking things?
Nope. Question is, and I'll paraphrase it back to the simple question that I want to answer. No, is that how do I think these pieces come together in terms of crop residue, soil temperatures, soil water evaporation, and how does that really benefit us in drought years like this year? And where's that water coming from that made that crop so successful this year? Is that a good paraphrase? Okay. So if you look at this, again, that residue layer out there, all that energy that's going on coming in from the soil or the atmosphere is absorbed at the top layer of that residue, maintaining a very cool environment, limited amount of energy going into that to evaporate any water, so we keep it very moist, we keep those roots near the surface. But we also have got a different system going on that we haven't talked about. I think Jim will talk about it this afternoon, is we have water stored within that lower profile that actually moves up. Capillary flow moving that up, so we're beginning to feed that root system and everything else. You begin to look at these dynamics and saying, what's going on between the biology within that soil, the root system, not only for the uptake of nutrients and water, but then how does that crop utilize dew and stem flow coming back down, because you see a real wetted part of that root system right near the roots that are the root ball of a lot of cover crops. And we see that, but we don't really think about that. It's very important, but in reality, over time, it is important. All of these pieces come together and saying, if I modify that microclimate, that soil microclimate, to make it much more effective for that plant to grow, utilize the resources that are out there, and reduce the levels of stress, so I don't go from no stress to hammering that plant, which is what we often do, is that you keep that plant much more in an even keel. It just works a lot better. Just think about it. If you worked 24 hours, then slept 24 hours and worked 24 hours, what would your life be like? It'd be nuts, wouldn't it? I mean, we often want our plants to do this. We say, you know, we want it to be really respond quickly when things are right, and then when things collapse, they just collapse. But if we can keep that plant on an even keel and running a marathon, the better off it's going to be, because it becomes more tolerant to the stresses out there. There's a lot of work on preconditioning in terms of water stress. There's a lot of things that we go on that we don't fully understand about how plants respond to stress and how they cope with some of these stresses, because we tend to look at the episodic events that are kind of the hammering things. But if you look at that slow piece of how they adapt, much different puzzle of how the plant responds to anything that we do to them. And I think this is part of that puzzle, is how do we begin to look at it from that perspective. There's a lot of I'm excited about agriculture, to be quite honest with you. I'm excited about the way in which we can begin to look at this system, but I do think we need to start looking at it much more creatively and with much more innovation than what we have been doing. And I think that becomes our challenge. You had a question.
Yeah, you spoke about the importance of protecting against high extreme temperature, but what about the importance of managing cool temperatures? So temperature, microwave activities relate to temperature, right?
Sure.
So how important is that early season management?
Oh yeah, I mean, obviously we all driven by a temperature system. How many people like to be cold? Nah. If you like to be cold, why are you in there, Minnesota? You know, but you know, if you think about this perspective, is that yeah, in biology, just like you and I mean, if it's cool, it takes a long time to get us going, right? Microbes are the same way. It's getting that warmed up, but also at the same time while they're warming up, is make sure that they have the water and oxygen that they need to thrive as well. And that carbon resource, that sugar resource. They need to be fed as well. Not only getting warm, but also be fed. Because if you're warm but hungry, you don't do very well either. So you got to think about this as an overall system. That's what I mean by the ecological system that we talk about. And so, yeah, but we're understanding now that a lot of those microbes are kicking in a lot faster than we thought during the cool season than previously thought. Down at 40 degrees and things like this, that wasn't 60 to 80 degrees. It was in lower temperatures that we're seeing a lot of response. And so how do we get them fed at that level to get their populations up and going? I think there's a lot to understand. Sad truth, soil microbiome, we probably know about 5% of the soil microbiome. Means that 95% we don't have an understanding of what's really happening yet. That's where I think the biggest challenge is going to be for us. With that, oh, yes.
One more question. You asked the question about adding biology, right? In my mind, you need to add fungal biology and food forest. Am I wrong?
The question is, do we need to add fungal biology? And the food for it is part of the biological system. And the economist answer is, it depends. Depends on what's out of balance. What is that fungal nitrogen or fungal bacterial ratio? And what are the fungi that are out there? And that's when we start looking at this saying, you know, we see all sorts of different fungi that are out there and they need to be expressed. So what's limiting their expression? It's just like what's limiting bacterial expression in a lot of cases. And I think those become the pieces that are out there. And I think that one of the big pieces that we need to work on is When we start looking at the things that are causing us problems and why we're not seeing a response, I think we'll gain a lot of knowledge from looking at the things that are not responding the way we think they should be responding, as opposed to always looking at the success stories. We learn more by looking at the outliers than we look at the mean, because they give us a lot of understanding of what's going on. They open a lot of doors for us. So with that, Paul,
Let's give Jerry a hand. So, yeah, if Jerry will be around, he's got to take out, but he'll be here till 12:30 if everybody wants to tackle him with some more questions. But yeah, there's a lot of good nuggets in there. What an amazing presentation. It's been said that there's more known about the ocean floor than there is about the soil microbiome. But yeah, I just want to recognize a few people. Quick lunch is ready. But Beau Popejoy, could you stand up and be recognized? Beau's with, he has Manure Solutions that his company has, and we've been working with him on different pit additives. So if anybody wants to catch him at lunch to visit with him. Also, Mark Wagner's here's a guest with Jim Martindale. He's been implementing some of these practices in Wisconsin. So if you want to bend his ear, he might not let you get a word in edgewise, but so with that, we're gonna break for lunch, and I'm gonna have Nate Gruber come up and have a prayer blessing for us.
I don't need some big fancy introduction. I'm just real hungry and I love to pray, especially with men. We do a Saturday morning men's group, and last week we had about 13 people there. So we get to a group like this of 120 guys. This is awesome. It brings, one of my favorite proverbs is 27:17. Iron sharpens iron. Iron sharpens iron as one man sharpens another. Well, I look around here and farmers sharpen farmers as one farmer sharpens another, right? Let's just bow our heads and give thanks to the Lord. In the name of the Father, Son, Holy Spirit, amen. Lord, we give you all the gratitude for us men and women to get together today. Lord, we just have to remember that we're just stewards of your land. All we are is renters. Lord, we just ask you to help us to use any of these new practices we might learn. Just open our eyes and our hearts and our minds to any way that we can, just continue our farming practices on this great garden that you gave us, Lord, and help us to this be a ripple effect out of this area from the things we learned today to help provide for all your people. We just once again thank you, and we ask a blessing over all these men, women, and all their managers, their employees, from the top to the bottom. We'll run the table. Also, Lord, we'd ask you to bless this food that we're about to eat, and bless all the hands that it went through, from seed to a finished product on our table today. In your Son Jesus we pray. Bless us, O Lord, these thy gifts which we are about to receive, through our bounty through Christ our Lord. Amen. Thank you.
We'll try to get it back on track. We're a little bit late, but we'll work with it. Wanted to introduce Jim Martindale. Well, I only met Jim about a year ago, and we quickly became friends. I didn't realize it till later, but Jim was a crop consultant in his previous life, or earlier life, and he knew Del Glanzer, which is a consultant out of Alexandria that got us started in the 80s and 90s. Just found out recently he's actually an engineer, but he's got a unique perspective because he understands equipment and engineering. He also understands soil biology very well, and plant health and how all that works. So he's got a unique perspective. He's the owner of Soil Regeneration Unlimited out of Wabash, Indiana, and also markets the Curse Buster tillage tools. So with that, I'll welcome Jim Martindale.
I hope you can all ride with us because right now the road's got a few bumps in it. So hang on for, I don't know what the ride's going to be like. Somehow during the course of the afternoon, I want you to hear from 3 farmers. And if you saw the 2-minute clip about profiling the afternoon, you'll understand that I wanted people who operate just like you on their own farms and to share their experiences. And my job is to basically fill in some of the underpinning concepts that they are experiencing, how it's being impacted through tillage and perhaps even microbiology. It's been a very interesting conversation this morning about microbiology. I appreciated those questions because you guys have really given me some insight into where this conversation might best ought to go today. So I appreciate that. And I want to say that what's the most important part of the afternoon is that you get your questions dealt with to the best of our ability. And that means that we are expecting to be interrupted. There's no more frustrating thing than to have a question, and when you think it's the right time to ask it, you can't remember it. So the best time to ask it as soon as it occurs in your mind, right? Just stick that arm up in the air or just shout it out. As you know, we're live streaming. So unfortunately, we are saddled with just one mic. So I need to make sure I can hear the question clearly, and then I'm going to repeat the question so that our online audience, which happens to be around the world, I found out, right now. The question. You can't hear me? All right, so I need to get that mic up where it belongs. Is that better? Well, good. Thank you very much for that first question. All right. Adam, our man on the scene. Are we ready? We're ready. Okay. 2 thumbs up. I guess we're really ready. So the first person we're going to hear from today is Nathan Brearley. And I'll back this video up just about 10 seconds, and he'll introduce himself to you. And we're going to listen to Nathan's testimony. This video is put together by Adam Widener, who is in the back doing all the controls and making this thing happen for people. And he went up there with tech and their drone and basically interviewed Nathan for a good portion of the day in the spring. So we're going to bring Nathan on through a Zoom connection at the end of the video, and then you'll get a chance to hear about what happened during the growing season and to ask questions of Nathan live while he's on the Zoom call with us. All with us on that? Same kind of protocol through the afternoon. All right?
My name is Nathan Brearley. I'm owner of Brearley Farms Incorporated. I have wanted to farm and dairy farm my whole life. Like, I would jump off the school bus and I could have my boots on and clothes changed before the bus was 3/4 mile away. My father and I own the farm together. He's basically said, you're gonna do better at this than what I ever can. You take it, I will help you. We milk 500 cows. We raise our replacement heifers as well. And for all those animals, we raise our own forages. We farm 750 acres, and all of those go to forage for the cows. In the last couple of years, I've been fighting tar spot in corn. For the last 10 years, I've had insects in our alfalfa. I've wanted to increase plant health, and it's very difficult to do that when you are feeding the plants a lot of commercial fertilizer, a lot of fungicide to keep away the disease, a lot of insecticide to kill the insects that you don't need. I knew there was a better way. I've made it my mission to learn more about how to make my system a healthier system, how to make it an easier system, how to not be handling so much chemical for myself, my family, my animals, my soil. And I came across Jim and a video that he had posted online.
Welcome to Advancing Health for Soils, Plants, and People.
It was like a 7 or 8 hour video. I watched it 2 or 3 times and I said, this here is a system that's gonna work for me. Like, this is what I've been looking for. I know that I'm not as good as what I should be right now, using fertilizer, doing full tillage, they don't foster the soil microbes. They kind of hinder what they're supposed to be doing. I'm harvesting forage, I'm hauling manure, all of those things have heavy equipment, just really pushing down on the soil. So I wanted living roots because the roots will help hold up that wheel traffic. But even that, I need to get seed into that soil profile, and I can't do it no-till. And I've tried every tillage tool out there to loosen up the soil, but all it does is compact it and rip roots out of the ground. I started looking more at the curse buster. I heard the name of the curse buster on a webinar that I was listening to. I'm like, this thing looks like it'll work. This curse buster tine enters the soil, lifts, fractures, and gets that sediment layer broken up. It has just that right blend of loosening, but yet not destroying. And it appears to be working really good. This is my first year out. The corn that's coming out of the ground right now is much more robust than when I was using chemical fertilizer in the past. So I have a field, it's a 100-acre field, and there's a couple squares out of this field where you can see this contrast between my old system of full tillage and the stand of corn is beautiful. It's nice and black. It's picket fence rows of corn, but that soil had no living roots on it from September of last year until May 10th when the corn germinated and popped out of the ground. That is a long time for soil to be bare. Soil biology is dying. Like, we are not doing what we should be doing to that soil. Like, Mother Nature puts a plant out there wherever. That's what God wanted us to do, was to have a plant, just like in the woods or the roadside, there's always a plant growing, feeding that soil. So as a farmer, I think I need to emulate what that system is. So it may look really, really good right now, where there is black dirt, and that's what a farmer thinks is the best, but we have to use too much fertilizer to get there. We have to push that plant with a drug instead of the soil feeding the plant. I've been trying to find that balance between chemical fertilizer and manure, and how much less fertilizer I can do to get an end product. Most of the advice that we get is from a fertilizer dealer. And they may have great intentions to want to cut back on fertilizer, but that's how they pay their bills. I knew I had to get to a separate group of people to get honest advice. A new rotation that I'm doing is corn silage to trit in the fall. Once that trit is harvested in the spring, then we plant a cocktail mix of 5 different plants: sorghum sudan grass, 2 types of clover, a hairy vetch, and Italian ryegrass, which all of those things will work together in harmony to help the soil microbes harvest what they need for the plant, and do that in a better way than a monoculture crop like alfalfa. Those plants are also more digestible for a cow than what alfalfa is alone. So we're using that instead of alfalfa in our diet. With that cocktail mix in the summertime, we will cut that 4 times. First time will be about 35 days after we plant it. At that time, we put fresh manure down on the soil, so we're cycling our manure. And then after we cut it, each time, we put a little bit more manure on every time. So we're cycling that manure nutrient immediately into a living crop and getting that into a forage crop. All my other crops are getting cow manure as well right before planting. And even my triticale, as it gets planted in the fall, we haul fresh manure on it throughout the fall and winter time, and even early spring, to feed that crop manure instead of commercial fertilizer. With our manure, we're treating it with safe manure. That's a product that helps to make that manure more available for a plant and for the soil, healthier for the soil. It also helps with pathogens in the manure some, so that we can harvest that crop and put it into a cow in a safe manner. It doesn't have as much of those harmful pathogens in that manure as it's going to forage in a quick fashion, because we could literally haul manure and 30 days later be harvesting that crop, and I don't want to be feeding cows manure. There's a way that we can monitor how the plants are growing. Tissue sampling has been something that I've used, and it's helpful, but there's also this testing called SAP testing, and that I think is a more representative snapshot of where that plant is and what we need to do to feed it more appropriately for the rest of the season. I'm using biology next to my corn seed with Pacific Grow fertilizer right at the furrow. I'm putting 28 next to the corn like I used to, running about 15 gallons of 28 with the planter and some sulfur. And then I'm letting that corn take on whatever it has for biology, soil, that little bit of fertilizer, and I'm gonna run that all the way through the season until the corn tells me it's ready for more. Just like I help my cows out when they're not feeling well, I can help these plants out the same way. I just need to do testing on it before I just throw a bunch of stuff at it and hope for the best. It's just us as farmers doing a better job with what we were given to manage. I like challenges that can work if you just put your mind to thinking a little bit differently. I'm excited about the changes that we've done and really looking forward to the future on how much more this will progress and how much better I can get the system than what I used to have it.
All right, Nathan, thank you so much for being able to join us. It's great to have you. I hope the septic project won't be too troublesome after you've delayed your attention to it. All right, very good. Can everybody hear Nathan okay? All right. Do we have any further, well, one of the things that, you know, because we did all that video work in the springtime, you were still planting and so on. Of course, what kind of a growing season did you have, and how did things turn out, and first time experience? Maybe you'd like to bring us up to date a little bit first.
Yes. So I've only switched over my system a year ago now to really focus on a lot of the soil health principles. And this spring was the first growing season to get started with 23. And throughout the season, we had some challenges, like every year there's challenges. But what I noticed throughout the season was a very even crop, which we didn't have a lot of big rains in the spring to slow it down. So it's attributed to that, the evenness. But all throughout the dry time, just really saw that even across the field. And when it came time for harvesting, the chopper is my gauge for how things are going. And I could feel in the stick just that consistency across the field. And then another confirmation that I could see with consistency was the clay hills in our fields that usually yield less. They yielded very similar, and we had enough extra corn this year to have a combine come in and harvest our extra corn. And with that yield monitor, we had mapping capability on it. And I rode in the combine a couple rounds with a custom operator, and I could see that the hills weren't even really giving up a whole lot. 20 bushel maybe off of a 240 bushel average field. So I was really happy to see that even those hills were very strong, where they would generally be 150 bushel yield. So stuff can happen really fast when you really intentionally start doing things better. I'm pleasantly surprised on how fast that could go. When Jerry was doing his talk, he was, I got asked the question, somehow the question came up, do you need to add biology? And no, you don't need to, but it depends on how fast you want to get there, of how fast you want to feed the big elephant in the ground, and how many years you want to take to get it there. And I don't like waiting. So I like using biology to jumpstart everything. And just this first year, it's really exciting to see the improvements of changing to what we're doing now. And change is really hard, but when it's done with the right purpose, the right knowledge, it has been really fun this last year.
Most of the guys in your area has some issues with weed control because of lack of early rainfall.
Yes.
Herbicides activated. Did you share that experience or not?
No, we're more of a contact weed control environment.
Okay.
So when that weed comes up, I knock it back. Liberty is what we use this year in our programs. And this coming season, I would like to use some more light residual chemicals along with contact to do weed control issues. But yeah, there was some guys that were doing pre-emerge where their program suffered because it didn't get activated.
If you have something else you want to mention at any point, Nathan, please let us know. I don't see any hands. I didn't think these guys were bashful. Okay, we got a question from live stream.
Correct. Question from Christophe Popejoy in France.
You want to come up here and read it? Paul, come on. We'll get this one time, right? We'll get it right.
So pretty cool. We got a question from France. How to keep the soil truth cold season beneficial for microbes, and how to switch from cover crops to crops without chemicals. Have you understood that?
Say it one more time, please.
English is the second language, as you can tell, right? Christoph, I hope we get this right. Say it again.
So a little bit of language barrier, but how to keep the soil truth cold season
through
the cold season beneficial for the microbes, and how to switch from cover crops to crops without chemicals.
Understood. So that is some of the things that I also had questions with going to a different system, more of a green all the time type of a system, and the chemistry part of how to slow down or stop your in-between crop when you want to go to your intentional crop. Or in our case, how we just go from one forage to the next forage, depending on whatever season is ideal for that to grow. And without chemistry, you need to do some tillage is the only thing I could think. And with our tool, the Curse Buster that we have now, I think it can be done where you can knock back that growing crop enough to then let your intentional crop thrive. And then if they want to grow together, that's great. You just want to make sure that the crop before your intentional is the right species to grow together.
So I avoid chemistry. I really have an aversion to early applications of chemistry because I know that all chemicals are essentially mineral chelators. The reason they work is because they interfere with enzyme systems within the plant by tying up a trace mineral. And that's the last thing I want to do to my crop that I'm trying to grow, is hinder in any way its mineral access. And so in Nathan's case, the triticale goes right into a forage. So it doesn't matter that the triticale recovers and grows within his, is it 5 species? Is that right? The cocktail mix?
4 to 5 species of
4
a
to 5.
cocktail mix.
Yeah. So that's kind of a walk in the park in that transition, which would work for some of you guys that are in dairy here. If you're thinking about various rotations and multi-species as a forage crop for dairy cattle or beef. The other situation you were talking about was when you were coming out of alfalfa and going into corn. And that was really, that could be a struggle because you got a plant that does not want to die, right? Any alfalfa growers in here? Oh yeah, bunches of you. So, okay. I hope that helped you, Christoph. And questions here? Okay, way in the back. The question, Nathan, relates to the 100 acres, you know, where you had some of it was conventionally tilled, no cover, you know, lots of brown ground. And the other one was where you were planting behind the triticale harvest.
Yes.
You remember we were there and saw the difference in the early growth and how did it turn out? You want to comment on that?
So there's a couple things to note about that. Early season, the bare dirt looked like it was thriving, and it was. Like the plants were bigger. They were visibly bigger. The corn that I planted after triticale was way behind.
It was measurably bigger, right?
Measurably. And I was like, oh no, what have we done here? Like we're starving this corn because of the trit being a grass, because the trit loves whatever the corn loved, and it stunted it. Like it is really behind. And is this living root type of thing the way to go? Should I have planted corn after triticale? I was asking myself all these questions. And then as the season went on, the heat turned up throughout the summer and the rain shut off, and both of them were struggling the same, I would say. We started getting rain in July. The bare dirt took off. And finally, the trit stubble took off as well. So they were both off to the race, and the bare dirt was ahead by a long shot. And as we continued to get more and more water, that bare dirt soil started to lose the race, and the triticale ground came to life, that stubble where there was corn. And in the end, the corn that was on the bare dirt was a couple foot shorter. I didn't do any yield checking on it, but the ears were pitiful. And the stuff that was in the middle of the field was a respectable yielding corn. I didn't take a yield of that corn because it went to snaplage for feed, but it was very even, very respectable. The headlands were a joke. So, and the edge of the field. So it was headlands and edge of the field that were bare dirt. And it was essentially when I planted the trit the year before, I didn't plant trit on the headlands, and I saved like 5 acres on the east side of the field where I ran out of seed. And those were my check strips. And definitely that triticale added to the water infiltration, the biology. It was staying alive longer the winter before. And when it got tough, especially with that water infiltration, that's when it really kicked in and it paid dividends.
Great. Okay. Another question. Go ahead. Okay, I guess the question concerns the triticale going into corn, Nathan.
Yes.
How big was it when you cut it for forage? Number one. Was there any regrowth when you planted the corn into it? And if so, did you chemically control the triticale, or did you just let it go, or how did you deal with the second growth of the triticale?
So the trit when we cut it was flag leaf stage. That's when we cut our triticale, is for lactating cow feed. And then when we plant corn, we're targeting for as soon as possible. It could be hours from when we take the chopper out of the field to as much as 3 or 4 days. And I've planted corn after trit immediately, or I've waited a week, and I've tried to do manure before planting and manure after. It really doesn't matter. When the conditions are right to put seed in the ground, that's when you do it. And then if you want to put some manure out after, that'd be great. As far as weed control or regrowth control, I just wait until it has enough regrowth that the chemistry can touch it and set it back or kill it, and that it's not taking away from the corn, that it's not rubbing on that little plant, it's not competing with it, because they're two grasses, and the sooner that you can get that triticale out of the equation, I think the better for corn. It's almost like if you had foxtail growing in your corn, or another grass growing in your corn. It's very competitive, so you want to get it away from it as soon as possible.
Did that handle the question okay? Okay, very good. Nathan, because we're kind of crushed for time, I'm going to let you sign off and go take care of that septic problem over at the parlor, and express our appreciation in behalf of everybody here for letting us take some of your day, and appreciate your insights and especially your motivations to do a better job. And I could go on for quite a while talking about how you care for your cows. It's been quite an education to spend some time with you, and I really appreciate it. Thank you very much.
You're very welcome.
God bless you in the new year.
God bless.
Bye. Okay. I'm not sure where I go next. All right. That's not it. Boy, I got to clean the deck here. I hope I can find myself. All right. Now, one of the things which Nathan, as you recall from his description of how he deals with manure, it's a big part of his program. And so, as you heard him talk about, he treats his manure, and it's because we basically have set our sights on creating manure as a microbial resource, not just inoculating soil with whatever is in it mineral-wise and certainly carbon-wise, but also microbial-wise. And so it was that I introduced him to our next guest, Beau Popejoy. Beau heads up New Solutions Ag in Fairbury, Illinois. We hooked up about 4 or 5 years ago, I guess, already, something like that. Is it 6? Oh my goodness, time's getting away. And I want Beau to share with you a presentation that's been condensed from about 60 PowerPoint slides down to a half a dozen. And he's only got 10 minutes. I hope if you wanted to talk to him about this, you did it over lunchtime, because he also has to leave fairly early to get back down to Illinois. But Beau, would you come out and tell us a bit about how this whole thing works with making manure a better resource, okay? Let's see if I can figure out how to get out of this and get into you. You know how to do it here? Oh, it's right down here. Isn't that it? Manure one, all in, right? That should do it. As you probably noticed, Nathan called it safe manure. It's actually gone through a name change. So Manure One and what Nathan was talking about are the same thing.
Thanks, Jim. Everybody hear me okay? All right. Yeah, so we're going to be talking about Manure One, but some of you in here know it as safe manure, so just ride with me. And like he said, we're kind of on a time crunch, so I'm going to blare through this a little bit, probably way too fast. So if you got questions or anything, I'll throw my contact information up at the end, and feel free to get it down. I've got cards and stuff over here as well to take with you. So the reason I'm here today is to show some experience that we've had with Manure One, a new case study that we just got done out in California, and to give you a little bit of history on this product. Me and Jim started working together about 6 years ago for fertilizers and also within manure, and which was started as safe manure and now has evolved into Manure One. And to just kind of put it in a nutshell, what we're trying to do is we're trying to create a more biologically active manure, right? And to say that out loud, people are like, well, isn't manure already active, right? Well, in most cases, yes, but what's in it, right? What microbes are in that manure? What's the fertility value of that manure? What's it do when it hits the soil, right? And we're all out there spreading manure at different rates, whether it's swine, whether it's dairy. And what we've been able to do in the last few months is kind of circle around, take some of that information through biomakers and some of the DNA in the soil, some soil DNA testing, and show you on a large dairy, Taveldi-owned dairy, Lone Oak in Hanford, California, kind of what we were able to do on a lagoon out there. So I won't go through my history. Just feel free to reach out to me at any time. And we'll go through this. So this was done in Hanford on a 54 million gallon lagoon in the last year. There's 4 of those on the same site. So they're storing 200 million gallons of manure on one site, 2,000 some feet long, 150 feet wide, 40 feet deep. So lots of manure. I've never seen 9,000 milking in one place before, but they do it, and they do a lot of it. So the reason we were called in was digesters. So they're 6-7 years in on the digester program out there, and what they're starting to see is their yields start to do this. And some of the locals around there have been trying to figure it out. You know, what's going on? Why are we seeing yield drop here? And kind of pointing the fingers at, is it the agronomists? Is it, fertility options that we're using? What's really happening? And a few of the guys in the fight had mentioned, what's coming out of this digester, right? So we were brought in to reactivate the biology as it comes out of the digester. So as the manure is coming through the digester, obviously we're getting the material to gas off. We're getting rid of some of the carbon out of the material. It's a very anaerobic material when it leaves the digester and goes to the lagoon. And what we've seen is over time, as that manure gets land applied at high rates, we're starting to see an effect in yield. So we've got a lot of tied up nutrients out there. Biology, it's not really solubilizing those nutrients, and the plant suffers, whether it's in stress, with nutrient cycling, all those sorts of things. So this is the result. So what we did was we took 2 fields where we had a control lagoon right next to it, and we had a treated lagoon where we took the material out, land applied it. We waited 30 days for it to kind of take hold, and then we did biomakers DNA analysis on both sides, okay? We took multiple samples throughout the blocks, sent them into biomakers. And has anybody in here had a biomaker study done yet on their fields? Besides Jim? Okay, I recommend it, and we'll show you why here. So this is the lagoon itself. So the application, to give you a little bit of idea of the application, is we broadcast it in the lagoon. It goes in one time, okay? So the product is not just a microbial, it is also a fertilizer / biochemical as well, okay? So we've got a combination of material going in there, which it's a selective strain of biology that we're adding, as well as we're adding a patented material to help feed the biology, okay? A lot of people are applying biology. It's been asked 3 or 4 times today, do we need to put biology in the soil? I can tell you that there's a lot of people selling biology to put in the soil, and it is beneficial to put it in the soil. I can tell you there's a lot of people that don't know how to keep it alive once it's in the soil. So it's a for one-time application, it's there, and what do? They just keep applying, keep applying, keep applying. So our goal with the product is to apply the material one time and give it sustainability through the 12 months of the season before pump out, and you've got an army of beneficials that you're taking to the field. So this is 2 days post application, so you can see there's totes sitting on the side. What we do is we broadcast it over the top of the lagoon, and you can see just 2 days after putting it in, you start to see a lot of degradation in the material. As we put the material in, it amplifies not only some of the biology that's in there, but the biology that we're adding to the material. So this is some of the stuff that we were checking and that were their concerns. Obviously, solid reduction is huge when it comes to dredging. When you dredge a lagoon that big, it is not cheap, okay? So any way we can get rid of sludge, any way we can create a more aerobic system, aerobic manure instead of anaerobic, presence of oxygen. So we were checking DO levels, making sure that, yes, we were bringing the dissolved oxygen level up in these lagoons as well, which was important to them. And just overall, they were impressed with the solid reduction in total. They got about 10 feet of sludge out of this lagoon in 1 year. So we'll go over to the bee crop test. This here is going to show you, and I apologize that it's kind of small on the screen, but I'll go through it. So on the control side, we look at total biodiversity at a 1.77, and in the treated side a 4.38, okay? It's a scale from 0 to 10, just total biodiversity in general, and then they kind of break it down. And what I like about it is we talk about auxin production and cytokinin production and stuff like that, but what really does that do, right? So the bee crop kind of breaks it down. Auxin production is towards cell division and stem elongation, and they kind of break it down into terms that you can understand, in which I know most of us, me including myself, have a hard time going through some of these terms sometimes and understanding what each one does. But we get into the microbial populations, and it shows you your fungal versus your bacterial distribution. And within the phylum, I really look at the bacteria side with what I do. In what are those phylum distributions across a control field versus a treated field? Now, what I would look at that I circled there is the total species. So on the control side, we got 579 different species that were identified, and they are all in this, but it'd take me a half an hour to go through every page to see every single microbe that's identified in these things, but it gives you a pretty good idea of what's going on. In the treated side, we had 701, okay? Now I can tell you that we're not adding, 122 different microbes in this consortia. So what we're seeing is by augmenting the manure, we are seeing biodiversity increase across a lot of different species, right? So one of the main ones that we're going to notice here is the firmicutes, which is essentially bacillus, okay? 9% in the control, up to 72% in the treated samples. This gets into stress adaptation, very hard to see, exopolysaccharide production, which is salinity protection. A lot of people are dealing with salt. That's a big concern of theirs in California as well. Salt binds soil. It causes a lot of issues. So we're attacking the salt as well. And this is the top 30 of the microbes that are identified out of those 500 in the control, okay? And what I want you to notice is that I've highlighted a few of them that are nitrogen oxidizing microbes, volatilizing nitrogen to a gas, right? And losing in the field is some of the top, most prevalent and dominant in the control side of the system. Off to the left, when you see the blue squares there, what they will identify for you is the CDFA approved microorganism list. So if there's one that's approved for application, it would be lit up in blue, okay? This is the treated side, okay? So all of a sudden we start seeing a bunch of blue blocks in the treated side. And really, I can just get into some minor details on each one of these strains and what they do. But as we see the two most prevalent ones, Bacillus cereus and Bacillus megaterium at the top, Bacillus cereus is really known for creating biofilm. So when we digest material, when we digest manure, one of the end products of that is acetic acid. And acetic acid is essentially the trigger mechanism for creating biofilm at the root, which creates this exchange that we've talked about all day long. We also have bacteria that are in the soil that produce acetic acid and create biofilms. So it's, for me, very important to see very high amounts of those species that create acetic acid and create biofilms within the soil. So, but what we start to see here in a nutshell is we start to see that not all these microbes are in the consortia that we're using. Most of them aren't, right? So we start to see species become more prevalent just by adding other species, right? If we looked at the control side and looked way down the list, you'll probably find Bacillus cereus in there at extremely low level, right? But what we're doing is influencing a change in the ecosystem within the soil by treating the manure to increase populations of beneficial microbes. As we increase the beneficials, what do we see? We see yield, we see better plant health, all those sorts of things. So the Biomaker study is a great way in your program to go out. If you've got some issues that you're trying to figure out, you can go out there, take samples. It's not a cheap test, right? None of these are. You're checking DNA and soil. But it's a great way to see, what do I actually have out there? How many of these are beneficial? Do I have, some problems with, some different things that I've been having, trying to figure out? And you can really just get a motion picture of what's taking place here. So we broke this down into percent increases just to make it a little bit easier. So fermentation was up around a 400% increase. Firmicute population, which is your Bacillus, 600 to 700%. But we look at a few of them. Biodiversity, for one, it was around 140% increase in biodiversity in the soil. And then look at salt tolerance, an 800% increase in salt tolerance. We're using salt digesting microbes within manure to produce potassium through biological transmutation. So we can solve salt issues in the soil. We always have been able to do that, whether it's strawberries, coastal conditions, all that sort of thing. When you start introducing these microbes into manure, we can now digest salt manure, which I know everybody in this room has dealt with salt manure. So very important to those guys out there. This is some of the volatile fatty acid testing that we've done through the years. Just showing that the more we digest material, this is actually swine waste here, that the more we digest material, the more we increase acetic acid. And then I pointed out that Bacillus megaterium secretes organic acids that cellulose phosphate. They also produce acetic. It's an acetic acid endophyte. So all important things to where we follow this acetic acid increase in the manure to the soil. All of a sudden we bring the ecosystem more in line. We track the nutrients as well. This is in Hanford, so from 5.5 pounds of total TKN to 8.4 post-treatment. People ask how we do that, and I'll show it to you here real quick. And we track the fertility value of that, just using chemical fertilizer inputs and prices of chemical fertilizer and transferring it into the value of the manure. So this is an untreated value of the manure. This is the treated value of the manure post-treatment. So 366,000 to 620. You can see the investment there and the added value, $196,000 in treated value. When you got that much manure, they're concerned about the manure more than anything on that farm that they're feeding tree crops and things like that with. So how much time we got, Jim? That's it? Okay. All right, so a little bit of gas sequestration that's been done through Berkeley. Third-party testing, it stops methane, stops hydrogen sulfide. It's selective. It increases nitrate reduction. So as we increase nitrate reduction, we see a pH shift. The pH shift in the manure, as you can see, it's shifting up 8.2, 8.4 in some cases. We drive the system away from methanogenesis and sulfate reduction. So as we lower odors, we actually lower ammonia production. We keep everything in the liquid phase. We increase the nutrient value of the manure, okay? It's EPA approved for methane reduction, the only one so far in the United States that's got an EPA exemption for reducing methane. Third-party pathogen testing, like Nathan was talking about, we are lowering total coliforms, E. coli, fecal coliform within the manure. That's as we get the system more in line, you see a natural reduction in those pathogens. We're also a nitrification inhibitor, so if you're using one, there's no need to use one if you're using the safe manure product. Why is that important? Obviously, everybody's seen pictures like this. Nobody wants to see it on their farm, of course, but we see them in the news. And if you don't have manure, we do a lot of the same products. We bypass the manure and go directly into your 28 or 32 program if you're using that. And we're adding calcium carbon and a lot of the same benefits that you just saw, bypassing the manure system and going directly to the field. It's called carbon 27, which we've got over here. So any questions? Sorry, that was, yep.
Explain why Nathan, like, he puts manure on after he takes the crop off, and why he's able to harvest that crop, you know, within 20 days or 30 days after that.
Yep.
Because just putting raw manure out there.
Yeah.
Tell him what it does to the crops and stuff, and you don't literally torch the field and turn Snow White.
Yeah. So why, repeat the question, I'm sorry.
About why Nathan, when he's spreading manure, why he doesn't take raw manure and put it on his field, and the damage that's done from just raw manure with the salts and
Yeah. So everything's in a more plant available form. Yeah. When you're putting this material into manure, it's digesting the material and creating a lot of amino acids and a lot of different things like that. It's not as hot, right? So you can put it down on a crop and not burn it like you would typically burn, you know, by just taking straight manure out there untreated. So I hope that answers. Yeah, exactly. Yeah, and the increase in the microbial populations, you're talking about taking a product and putting it in that has the ability to replicate every 30 to 45 minutes, and it's in there for 11 months. So you can imagine the quantity of beneficial microbes by the time you take this material to the field, and the balance of the pH, all those sorts of things. It's amazing what microbes can do in the presence of soil when they're in abundance. So, yeah, just cut. Exactly right. It's ready to feed. It's a plant available form. Exactly right. Yep. You got it. We use straight biologicals in that. The patent we do not use in dry material. It will off gas in that environment badly. Don't try it. So yeah. Any others? Thank you, Jim. Thank you, everybody.
All right. Let's see. What do I do here? I'm going to spend a few minutes talking about trying to draw together some of the pieces that you've heard from Nathan and from Beau, and bring us into another interview with another cursebuster user who's got more longevity. And we'll do an interview with Carl Brubaker at that. So one of the things I want to try to point out is that the biggest resource that we actually have in our soil is microbiology. And everything that we do should center around securing the future and the propagation of the microbiology of our soil. The fact of the matter is that once we experience imbalances and problems in the microbial world, your plant begins to know that instinctively, and we call it disease. Jerry talked about stress. What moderates stress is the biological influences that the plant is experiencing from the microbiology. Can you grab that? It's like the thesis that your immune system is actually centered in your digestive tract. Have you heard that? All right? We got the same issues. That soil is essentially the digestive system. It's also a reproductive organ. And so microbiology is right in the center of what happens there. And what we do as managers has a profound effect because we change the ecosystem in which this living organism has to function. There's a bunch of them out there, about 6 billion in a teaspoon of soil of these microbials. They exist, and this is very interesting new information. They exist as a part of the legacy of the crop you grow to produce a seed. They literally, microbes, organize themselves and live in close proximity to the germ of the seed that your plant is producing. And they also inhabit the bran and the endosperm area of the seed. So literally, that seed that comes out of that pioneer seed bag carries an inheritance. And it's microbial in its nature. Dr. White has gone so far as to suggest that the source of genetic progress that a plant may exhibit through adaptation to an ecosystem or an environment is attributable to the influences of these microbes that visited the life stream of the plant that now become deposited in the seed. Getting the idea? That's how central microbial communities are to what you're producing. They exist, of course, in plant material and crop residues, of course, in animal waste, which we've now talked about with Beau. Both domesticated wastes and indigenous animal populations, like birds, vermin of various types. They're all carrying genetic information in the microbial discharge that comes from the life of that animal. All right, Beau. All right. There are basically three sources of plant nutrition. Of course, we've talked about mass flow, soluble nutrients that are taken up as water takes up, as water is absorbed by the plant, delivering soluble minerals into the plant material. The one we want to focus on right now is number 2, nutrients that must be oxidatively extracted from soil microbes within root cells. Ivy Chang, whose picture is up there, is one of the graduate students in James White's laboratory at Rutgers University. And I credit James with many of these slides that you're going to see right now in this series. Paul charged me with talking about rhizophagy. Can you all say it? Rhizophagy. Come on now. Rhizophagy. I want it to become a part of your vocabulary because, believe it or not, your farming future depends on you becoming knowledgeable about rhizophagy. As Paul said, plants are eating microbes. Okay? It's a whole new field, an exciting field. And of course, the other one is microbial nutrition supplied through mycorrhizae, which is a form of a fungus. And we won't go into them today. Basically, all of this is based on some very basic, fundamental root physiology that we need to understand if we're going to apply the information correctly. And number one of those is that each root tip, emphasis root tip, is where rhizophagy takes place. Each one of these root tips only push forward in soil through the influence of microbes, which it is consuming at the growing tip, and they only do it for 3 days. And then the root basically matures. It's like when you turned 18 or 19, you didn't get any taller. I start to get shorter, actually, at my age. I think I'm shrinking a little. But that root tip is only functioning, moving through that environment for 3 days. Bear that in mind when you look at a root system. What you are looking at in terms of root system architecture is the culmination of thousands of 3-day events. Get the idea? One of the take-homes that I want to give you today is that if you dig up a root system and you study the root system, understand you are looking at the culmination of a massive number of 3-day growth events from each one of those roots that you see. Okay? Are you with me? Number 2, new main roots or crown roots are expressed for only 40 days on an annual crop. And for most seed-bearing perennials, again, this annual event or once-a-year event is basically terminated at approximately 40 days from when growth is initiated, either germination on an annual crop or breaking of dormancy on a perennial, such as your pasture grasses or a forage crop. 40 days. We're all done growing roots this year. That gives you basically, right, 5 weeks, 5 to 6 weeks, and it's over for the season, except in between where those boundaries were set. As far as those root systems could go in 40 days has essentially set the boundary. If that root system moved this far from the seed in a strip till environment, and that's as far as the main roots or crown roots got in 40 days, that's as far as they're going to go. After that period, up to the point of pollination, or when reproduction begins, that plant will only fill in root systems within those boundaries. Got it? So it's not going to do you any good to run out there with an anhydrous knife or a ripper shank of something between the corn rows after 40 days and think you're going to put root systems out in the row center. The plant is not going to put roots out there after that 40 days. You may do some other things. You may influence some gas exchange. You may influence some behavior of water or something, but you're not going to change where the roots are. They're on a clock. When pollen drops, there is no new root activity at all. Period. End of story. When you don't want to be in a cornfield, root systems already stopped growing. Okay. Yeah, that's a soybean plant in a 15-inch row. And it is basically, as you can see, intertwined with other soybean plants in the other 15-inch rows. Here's an example of a plant which in that first 40-day period established some massive boundaries. I don't see very many soybean crops that look like this. All right, but there was no interferences, and microbiology was stimulating these root systems to continue to initiate. That's the role of hormones like auxins. Auxins are produced by bacteria to stimulate root systems to branch and to keep growing out, initiating new root mass. This is an example of a corn crop where there was very little restriction. You can see the depth, you can see the breadth. On this particular farm, these root systems, by the third year, it actually dissolved a 4-inch plow sole. Started at 9, went to 13, 13 and a half inches. And in the second corn harvest, beans between no cover crops, the plow pan was gone. It was dissolved by root system behavior. And as long as we continue to put roots there, it will never return. Okay? Feel free to interrupt me. Here's an example of organic soil and the idea of the hair roots along the sides of those and the soil retention. Beau was talking about biofilms. Biofilms are the communities of microbes which contact and actually mobilize nutrients from the soil particles. And when you see soil adhering like this, you know that these biofilms and communities are highly functional. They are accessing nutrients from the soil colloids in massive quantities. Literally, probably millions of miles of surface, millions of square feet of contact area in a root system like that. Versus this is an organic farm where there's lots of tillage going on. And you can see what's happened. The aggregate structure is totally collapsing. And the root systems literally just kind of move from one fracture zone to another, and that's it. And they never got more than 5 inches under the surface of this field. It was moldboard plowed at 10 inches. And then it was groomed again and again and again. So the structure was essentially destroyed. Now here's the research that Beau was citing, talking about the acetic acid and the very significant role of acetic acid. If you read way at the bottom of the abstract summary, it reads that we further demonstrated that one such volatile acetic acid is particularly potent in stimulating biofilm formation. Here's what's really exciting. I don't know what you'll do with this, but I hope you take it home with you. When God made the creation, he connected all of the events. As you've already sensed in your lives, things are cyclical, right? Things tend to repeat. Well, in the ecosystem of soil, every root system that grows decomposes. There are provisions in the soil microbial community, they're known as saprophytes, who are designed to digest that root mass. They're also designed to use those exudates that Jerry talked about this morning. And what those do is eventually decompose into various forms of acids. And if you're a dairyman, you've heard about propionic and lactic and isobutyric and butyric. All of these are fatty acids. You don't need to remember any of them, except for one thing I want you to remember. And that is that all of that, whether it's lignin, cellulose, hemicellulose, fats, oils, proteins, they all decompose to one substance. It's called acetic acid. And acetic acid is the very compound which results in new life. You getting it? Are you there? Anybody out there? You see the connection? Everything turns into the very substance that you need to have a new, healthy life. God's good, isn't he? What a designer. How long does it take us to catch on to all the details? Here's an example of a crop that, this is a lentil, by the way, grown in Saskatchewan. This plant is not even it's not even emerged from the soil yet. And look at the root system activity that's taking place. Here's what's happening. This is the whole essence of rhizophagy. We've got a diagram version here of a root tip. It is actually pushing forward in soil because of the metabolic processes that are taking place right there behind the root tip. What happens is, as that root expands and extends, it actually engulfs microbes. It takes them in and then produces enzymes and acids which erode the cell wall so that the plant can actually mine out the desired contents. Here's what's really exciting. The plant exudate actually dictates what microbes are supposed to be there to be harvested. Is that cool? When you pull in, they already got your meal ready. It's the right one, the one you ordered online, right? Then once that microbe is mined successfully, it is excreted where you see those 6 little arrows, those red arrows about the center of the screen. Those little hair roots that are formed are in response to the presence of spent or harvested microbes. And so what you're looking at there is 6 porta potties. Lighten up a little, will you? And those microbes, once they exit, actually are not dead. They actually reconstitute themselves back in the soil ecosystem and become the object of being eaten once more and being farmed out again. This is major, major source of health and nutrition to a plant. And the sooner this happens in the plant's life, the better. That's why I showed you those plants from Saskatchewan. Yes, question. Question was that, was I saying that whether the plant is looking for manganese or copper or another mineral or an amino acid or something, it actually is signaling the microbial world to supply that. That's exactly what I'm saying. Exactly. It's telling the cook, here's what I want for dinner. Okay? And it does that by engineering the exudate to create the growing environment to support that population. Is that wild? And these messengers were the same messengers that were around the germ of the seed and in the seed coat and on the bran. Okay? So we grew up thinking that, well, these crops are boron sensitive, or they are more demanding of zinc, right? When we talk about growing corn, we're always looking at zinc, right? When we're growing beans, we always think about manganese and copper, and, right? Well, these plants actually program themselves to get those priorities. And we have inductively learned from their response, that's why they're sensitive to that. That's a dictated trait that's expressed through microbiology. And it engineers the exudates to create the source. Cool. Okay. This is greatly magnified from Dr. White's laboratory, basically showing you the same thing, only this is not a diagram. This is a real root tip from a tomato. And it shows you this whole cluster of these microbes. You see the bacteria around the right-hand side at the edge of the slide? Those are all the bacteria that are amassed at the growing tip about to be eaten. And then inside, you'll see that darkened area. That's where superoxide and ethylene combine to erode the cell wall of the microbe so that the plant can consume the content that it needs. And it's all by design. It's not random. This is on purpose. And then you see the little hair roots on the other side of the slide. Those are the porta potties. Here's another shot of the same thing. Here's the interesting part, and one of the take-homes I want you to make sure you grab today. Paul cautioned me, guys have to use Roundup. And I don't want you to be too offensive about Roundup. I don't know that I could be too offensive. But at any rate, one of the things that I learned many years ago, and I've now seen, much to my gratitude, greatly embraced by many, and the fact that Roundup is a chelator. And that's why its most popular use is in paints to this day, because it controls the growth and population of bacteria and fungi on painted surfaces, so your paint doesn't peel anymore. You knew that, right? Okay. So you put some paint in your spray tank, right? So what happens is, one of its major minerals that it's actually attracted to, you always thought it was manganese, right? Because you saw the yellow flash in beans, the interveinal yellowing, which is a manganese symptom. Well, that's only because the bean plant manifested the manganese. That's all we could see. But if you actually did a sap analysis, you'd find out that it was actually iron that was really suffering the most. And it so happens that the most attractive metal for glyphosate or AMPA residue in soil is iron. Well, we got lots of iron. Unfortunately, we do, but not much of it is really available. Okay? So what happens? This is the process. This slide shows you the process of creating the necessary chemistry to actually eat the microbe. Remember I mentioned the word superoxide? There it is. In order to generate superoxide, you obviously got to have oxygen. And Jerry talked about that this morning, right? Soils that actually can breathe, they have gas exchange. Well, what's the exchange? The exchange is taking in some oxygen, giving up some CO2, taking in some nitrogen. So if this soil is not breathing very well, you may not have a lot of oxygen around, but even if you have the oxygen, you can't produce the superoxide unless you have the metal catalyst, Fe iron. Getting the idea? So if you're struggling trying to get root systems to look like some of the ones I showed you, you might consider testing your soil to see how much glyphosate in the MPA residue you have. Because if it's binding up the iron, you can't produce the superoxide to dissolve the cell wall to mine out the bug, the microbe. You see the chain reaction here? You don't have to take that home with you, but I'd suggest you do. and see if there is any way that you can avoid herbicides, especially those early in the growing season, when we're trying to set this whole system up to make this really healthy plant. Are we on the same page? No rotten tomatoes yet. No rotten eggs. So I think we're all pretty sensitive to the fact that herbicides are not always our best friends. Just another picture, the same sort of thing. All right, so the superoxide production requires iron as a metal catalyst. Soils contain glyphosate, bind up the iron, thereby potentially limiting the available iron for effective rhizophagy. And you can tell that under a microscope because you won't see the hair roots because the plant never had to go to the bathroom. It never successfully digested microbes. It may have eaten them, but it couldn't digest them. I have a question over here. Not that I'm aware of. It will have its impact. With a foliar, you can, with proper chelation, you can replace minerals that the microbiology would have liked to have supplied in an organic form, I add, right? Very readily embraceable, probably in an amino acid. But you can do some corrections with foliars, and that's one of the functions that SAP testing can perform for you, helping you to diagnose a hidden hunger, we called it, right? Better than anything we've ever had as a tool before is a SAP test.
I can tell you from firsthand experience that we thought we were doing everything right, we used glyphosate forever, and SAP test showed that our microorganisms were sorry.
Right. The comment, which I wish we had another mic because I love your comment, appreciate it. The comment was he's been using SAP test and seeing that reduction in micromineral uptake early with a long history of using glyphosate. Yeah, very good. Thank you for the comment. The next take home here is that soil with poor gas exchange, in other words, something that's waterlogged or has poor structure, poor aggregation, they usually present lower levels of oxygen present in the soil. So immediately you now have a handicap in terms of rhizophagy. Density layers, whether God-made or man-made, and we'll get into this in a second, minimize or eliminate metal chelators as much as possible. Those that love iron. Unfortunately, glyphosate is not the only one, and other weed control chemistries control and chelate other trace minerals. So to the extent that you can, and Nathan's actually doing this because he tries to use contact material as much as he can rather than soil residuals. And we're actually looking on his farm, we're looking at some older chemistry, which has a known history of less interference with plant nutrition. So the sphere of influence that we're trying to deal with here includes fungi and bacteria. We actually are trying to produce a balance in the microbial community, including the fungi and bacteria. I had to repent not long ago, thanks to Dr. White. I was under the understanding that if I introduced beneficial bacteria and beneficial microbes that were known to be health imparting, that they would go into soil if I applied them like Jeff asked about earlier, that they would destroy the pathogen. You ever heard of chitinase enzyme? No. It's all right. It's an exudate from the Bacillus megaterium and amyloliquefaciens. And it destroys the hyphae of a fungus that's pathogenic, better known as vomitoxin-inducing or scab-inducing Fusarium graminearum. And I thought that was the action. But Dr. White pointed out to me that that's not the action. The real action is, with the proper ecosystem and the growth and reproduction of these beneficials, the attitude of Fusarium graminearum that would give you head scab in wheat and barley and oats and vomitoxin in corn changes. Instead of being a drunkard on Saturday night, he shows up in church on Sunday morning. A transformed life. Thank you for the laughter over there. I love it. I'll see you next Sunday. It's literally the influences of the beneficial microbial organisms in the soil ecosystem reform or transform the pathogenicity of known pathogens. That is some of the groundbreaking work coming out of Rutgers University, of all places. You like that, Jake? I love it. It speaks of the mercy of God. It really does. I mean, right? When we come to God, we get a transformed life. When we maintain the ecosystem of soil properly, we have a transformed microbiome of soil. Pathogens aren't even a problem anymore. This is one reason why Nathan has been so amazed, because he's been a tar spot farm for 10 years. He's been spending fungicide money like it was going out of style. And we didn't touch those plants this year. But they had a different environment when they were born. Everything changed. Anyways, it's the source of epigenetics or genetic progress. It's the source of disease suppression. Seed integrity, we were talking about the colonization of the germ and the endosperm. It's absolutely critical that that environment exists. And we're already after 2 o'clock. My goodness. Microbes colonize germ and seed coats. Okay, let me see if I can't get done through here pretty quick. All right. We're going to sign me off of this. And let's see if I can move us on, Adam, into the next section. Please feel free to get up and go. We're going to listen to Carl Brubaker from Ontario, Canada.
Soil School on RealAgriculture.com is brought to you by the Ontario Soil Network.
Bernard Tobin here for RealAgriculture.com. Hey, today we're talking soil with Carl Brubaker here at his farm near Arthur, Ontario. Hey, Carl, how's it going?
Good, good. Thank you, Bern, for coming out.
Hey, and thanks for the invite. Hey, before we dig in, let's tell everybody a little bit about the farm. Give us a snapshot.
Okay, well, the farm is basically hog and cash crop. We have a 3-crop rotation: corn, soybeans, and wheat generally. The odd time we get some edible beans worked into there. So that's basically it. Some of our soil gets manure, some of it doesn't.
So we were talking before we started the video here, and you know, about 5 years ago, you basically said, hey, it's time to put away the plow here. We've got to focus on soil health. Why did you make that decision?
Okay, well, that decision was made looking at our fields, seeing what's going on, looking for something simpler than plowing, looking for sustainability to the farm, as well as a lot of research on what has happened in soil in the last 150 years. There's been a lot of change.
Yeah. Talk about your soils. Pretty variable here, right?
Yep, we farm anything from sand to some heavy clay, and most farms are variable.
Yeah.
And we needed an approach that will work on erodible soils as well as heavier clays that don't move a lot, but working towards sustainability and less tillage. A lot of erosion taking place, and quitting with that horizontal plowing and putting density layers into the soil, and working from the top down is just really exciting on those erodible hills and slopes, and yeah, great.
Now, part of this, I mean, obviously, it was changing your tillage approach. And actually, we were here on this farm 3 years ago.
Great.
Peter Johnson interviewed you about the Curse Buster, a min-till approach, or an implement that you started using, and you liked it so much you're actually doing some distribution. Tell us about it and how it fit your philosophy.
Okay, well, that's a good question. We had to do something. We weren't going to go straight no-till, and yet we wanted to cut back on our tillage. There's still density layers from being caused by rain. We tried to run the tool every 30 inches of rainfall because of the silt movement in the soil. Again, we did a lot of research and came up with this tool as something that fits what we've been taught in soil school, something that'll do what we need to do not, it's as much what the machine doesn't do as what it does.
Yeah, so it fractures the soil, but it really doesn't displace it or move it, right?
That's right. Yep. There's 10 inches between the tines, and that soil virtually stays in place, but it gets the side fracture. So it gets the air and water holding capacity improved, but your soil is still in place, so the naturals and all the beneficiaries can work, enhance the worm population and all that.
Now you had a lot of soil movement. We've got some great pictures, but now it's starting to stay put. And so talk about, what you're seeing in the field now, especially when it comes to managing tillage and managing residue.
Well, it's very simple. There's a mentality out there that we need to dilute our corn stalks and, mix it within 5 inches and things like that, which is really working against nature. The worms, etc., they like the stalks on top, and then they pull it in and they'll process it underground. If we mix it in, they won't touch it. It's got to naturally decay.
Yeah.
So back in the plow days, our corn stalks would be under the ground for like 3 years. They'd still be there. And now you can look at this field of edibles, the stalks were left on top, and where are they?
There's an old saying that you're not supposed to be able to grow edibles in a field like that.
Right. Well, we'll prove that wrong.
So tell me what's going on here. We're looking at the canopy here. I mean, you've got a lot of trash down there, sitting there. Looks like there's a lot of mulching going on. It just looks like healthy soil.
Yep. Yeah, the corn stalks were left on top. Obviously, we had row cleaners on the twin row planter. But this field this spring, I was out. I think it was like April, beginning of May. I was out one evening at 10 o'clock at night, listening to the worms. And they were working away.
Wow! And there's this great photo that you have of I think a shovel full of soil that you pulled up with 80 worms on it. Is that right?
Yeah, last spring. Yeah.
So I mean that wasn't there 5 years ago.
No, the worm population has exploded.
Wow.
Yeah.
Well, hey, let's talk about some corn here. And what I'm interested in is this great cornfield you've got here, and the roots. I mean, like the mass of root, the distribution of roots is this something you couldn't get in that soil 5 years ago?
So 5 years ago on fully tilled soils, we'd go to the field, we'd grab a plant, we could just pull it out. Those days are past. No longer. Now we need to dig out the plant. The roots are that larger and more established and going down for nutrients and drawn from a much greater area. Especially this year in 19, you'll find what they call pancake roots around.
Sure.
Density layer from a disc, whatever, and the roots are shallow because of the early rains. Therefore, we got to keep pouring the fertilizers on top to keep feeding the crop. Whereas we're trying to feed our crop with less fertilizer, feeding it from the bottom up. And a large root system is key to that. And also, what we're doing is leaving it decay where it grew.
Okay.
So that root system can decay, henceforth larger systems down the road, and we just keep going over top.
Yeah. So overall, I mean, like from a soil health perspective, you're still farming the same ground, but your philosophy's changed, your management practices have changed. Just talk about, I guess, that mindset change, and what's it doing to the soils here?
Yeah, great thought. So years ago, we used to bounce around on the plowed fields, and it's a big change, and it's simplified a lot. The fields are smooth all the time. There's no need to go out there to level it. From a systems approach, it's really easy to manage.
So it's simple, and from the perspective that you got a hog farm here, you're managing manure. How does that factor in?
We love managing manure with this system. The cornfield behind us this spring, we actually planted the corn, and then we put manure on top. And the manure's soaked in. There's no damage to the soil. We kept most of the nutrients. We weren't applying manure in conditions that weren't fit for manure.
Right.
As well as in the fall, we'll do a pre-till through standing live cover crop. We'll apply the manure, and after, and it just soaks in quickly, and that'll be our fall tillage as well. So, yeah, utilizing manure in our min-till system is fantastic.
So, final question for you: when farmers ask you, "Hey, Carol, how's your soil changed? What's the health of your soil now? What's the status?" What do you tell them?
Basically, look at the crops. Take a shovel full of dirt. Start down below. Look at those. See if you can find any density layers. Years ago, we could take a scoop and we could find the density layers. The soil would break apart in those lines. Yep. But now that we're going in from the top down, just side fracturing, those are disappearing. Soil is getting more curdy. Fields are getting more consistent. Those tough areas of the field are improving. And looking forward to the future.
Awesome. Everything's staying put. You got a lot bigger worm population. You just got healthier soil.
Yeah, we've taken lots of pictures of the spring floods and the difference. Even the snoil and the snert and the ditches and the road ditches, drastic. We've got photos of distinct lines between two different management practices, and it's totally staggering.
Great story today on Soil School. Thank you for taking the time, and as I say, you got a good looking crop and good luck for the rest of the year.
Thank you.
We've heard Carl talk about a density layer today, and we heard Nathan Brearley mention also about some kind of density layer, and Carl talked about 30 inches of rainfall. Did you all catch that? All right. This is the phenomenon that is known as microerosion. And Jerry touched on it today, mostly in context of gas exchange. And here's the phenomenon. The density of silt, soil particles, is almost identical to water. What we are doing when we put on irrigation water or receive precipitation events or snow melts is we mobilize silt soil particles from the top of our soil profile downward. When the water slows, it can no longer carry the silt and it drops it. The water may continue at a very slow pace through the plow layer, but it no longer is carrying the silt particle with it. So the macropores, where gas and water exchange, passing each other, allowing water to enter, air to leave, is now blocked. It's like a strainer. Okay? You dairymen know what happens when a strainer plugs, right? You got to change it. And so it is that soil naturally does this. And it's done this ever since God ordained that it was going to rain. Prior to Noah's flood, this did not happen because it never rained. The system operated solely on water coming up through soil, never moving down. And if you're a Bible scholar, you can go to Genesis 8:21 and you will read the account where God pronounces a curse on the earth because he has now ordained it's going to rain. There's your Bible lesson for today. There's more if you'd like the sequel. The house will be open down here on the corner. I don't remember the address. We can digress for the evening. But the point is, this density layer composed of silt is God ordained. And it creates most of your problems today, if not all of them, as the primary source of your issue. When you run a field cultivator, and that moisture level varies in your soil, and you've got your field cultivator set at 4 inches. Over here, the soil is dry enough, you can do it with no smear. You go down in that blacker ground and you run it at 4 inches, that's where your root systems will stop for 40 days. They will sit there and hammer on that smear. It was precipitated because of the density layer, which caused the water to sit perched above where that density layer is forming. And Carl Brubaker says we always run our tool after 30 inches of rainfall because at 30 inches his soil will transport enough silt that his density layer will be back and water behavior will be bad. And when his water behavior goes out the window, his gas exchange stops. You getting it? It varies. I've actually examined sandy soils that have 2 zones, one in the 2nd inch and one in the 5th. And a lot of times you can actually feel it. You take a tiled probe or a penetrometer and push it in carefully and start feeling at about 3 inches. Usually it's 3 inches to 6. It'll depend on the character of your soil, depends on a multitude of other unidentified factors on where it happens. But wherever the blockage occurs, you have a soil that's headed backwards because it can't breathe. Hello? We're really, really up against it on time. But all these charts right here, which identify the silt density location, are on my website. You can go there, you can find them. They're all recorded for you. Basically, all that we're talking about in terms of how I define tillage is addressing this density layer. If I can make this density layer ineffective, then I have restored gas exchange, which is the biggest nutrient the soil microbial community has. It's not your fertilizer. We spend all kinds of money on 5% of our problem. This is 99% of your problem. You can destroy it with a disc that runs deep enough. You can destroy it with a chisel plow. You can destroy it with a lot of other tools. But unfortunately, the side effect is almost as bad as the solution. Remember Carl Brubaker said this machine does almost as much as what it doesn't do as what it does. What he's talking about is avoiding horizontal motions through our soil, which produce density changes, which signal to a root system, we're not going any farther. This is it. Ken Ferry's been beating on this drum for 40 years. And he still doesn't understand this phenomenon. If he ever did, man, the sun would really come up. So this is essentially all that tool does. That's what the Curse Buster is designed to do. It doesn't move the silt layer. It just penetrates it and renders it ineffective. Hello? That's it. It's that simple. It's almost too simple to believe it ever really does anything. But it's amazing when you can breathe. I was thinking about it. I said something to Paul or somebody else maybe this morning at the house. I said, I think maybe I should just have everybody hold their breath. When they finally can't hold it any longer, raise your hand. It'd be interesting to see the variety of number of people, how you can hold your breath. Once we tell the microbial community to hold its breath or to sit there in water, we got problems. And this is a really incredible slide that I'd love to have you go study on the website, because this was done in the 70s. And it's a talk about really what happens in a waterlogged environment. Waterlogged soils produce a gas known as ethylene. You know it as a growth regulator. You spray it on tomatoes to get them all ripened together. We use it to make apples self-desiccate, right? We use ethylene all the time. It's a naturally created substance, and it totally deforms root systems. You put enough ethylene into a young plant's environment, and it'll never grow a deep root. It is not geotrophic anymore. And so, that early rainfall that we didn't get this year prevented this from happening. Your yield was being set in the first 40 days or less, and in the absence of substances like ethylene. That's why your plants continue to make progress. So we never threw up the roadblocks. We never took out the culverts. We never made speed bumps. It was smooth sailing because water was never a problem. Okay. Mark, we're going to have to pass. I don't know how we're going to do this. I think afterwards, Jerry, Paul, we need to open up for general questions. And so let's just do that now. And Mark Wagner is here with me from Middleton, Wisconsin. Mark is part of a family operation that milks 1,800 head, and he's first year experience this year with Curse Buster. And if Mark, if you'd raise your hand so people can see where you are. If you have questions you want to talk with Mark, then please go see Mark today. He's here in person to ask questions. All right, Paul. All right.
Thanks, Jim.
Yeah.
Well, thank you, Jim, and all the farmers that you had online. And sorry we couldn't get to you, Mark, but So I hope we picked up 2 or 3 things here today. There's a lot of information thrown at you, and if you're like me, you gotta sometimes hear things 3 or 4 or 5 times before it finally sinks in. So take this stuff home and ruminate on it. Ask us questions, and this is also recorded live stream, so we will. It'll be on your website for sure. What's that? Okay, there'll be a link as well, but otherwise it'll be on his Cursebuster website. So yeah, while we haven't endorsed the Cursebuster tillage tool, we like a lot what we see with it. There's a lot of good concepts, and we're really looking at it hard as far as comparing it to some of the other tillage tools we're looking at. So we really like what it does so far and what we've demoed. So we're gonna keep looking at that. So thanks, Jim. Yeah, and if anyone's interested in talking more with Jim and Mark afterwards, we have a short time here. I think we got to be out of here around 3:15 for sure. But talk to Jim, and you could meet at his Airbnb house if you'd like to. We got time after. So I know we've kept you a long time. We don't want to keep you any longer. Then also, if you filled out your surveys, you can either leave them at your table, or there's a basket up here, and there's also some business cards and other information up here. So thank you all very much for coming. It's been a pleasure, and I'm sure we'll be talking soon. Thank you.